Hello, everyone. Welcome to this first session of the last day of EGSR on material models. Before we start with the first paper, I should mention that the paper on practical ply-based appearance modeling for knitted fabrics will not be presented due to a last-minute impediment. But for now, the first paper of the session is a work from Eugene Deon. And Eugene is a researcher at NVIDIA with 20 years of experience creating digital humans. His research spans both deterministic and Monte Carlo methods for light transport with a focus on reflectance from rough surfaces and subsurface scattering. This paper is called an analytic BRDF for material with spherical Lambertian scatterers. And the floor is yours, Eugene.
Hi, I'm Eugene Dion, a researcher at NVIDIA. I'm going to talk about some work that I finished here, but also overlap briefly with my time recently at Autodesk. And the goal of the work is to consider a stochastic geometry of Lambertian spherical particles, which as we scale finer and finer inside a given object like a sphere or a teapot, to consider the limit as this microgeometry is so fine that we can't resolve any detail, and ask the question, what is the BRDF for this material? And in summary, the paper presents this BRDF in an analytic form. It accurately matches the underlying stochastic geometry. It's efficient to evaluate, not too much slower than competing models. And it's artistically easy to control with albedo mapping functions. You might be considering, why do we need a new BRDF? Well, if we look out into the natural world, we see a large variety of reflectance behaviors. And measured data can be really great, but it's a bit bulky and can be difficult to edit and control for an artist. They prefer parametric models, but no one parametric BRDF model can simultaneously match all the different behaviors that we'd like. So the goal of this work is to present a new analytic model that offers a behavior that we didn't have before. The popular GGX models that we typically use correspond to a random height field physical underlying basis, where the roughness parameter that scales the roughness of these models simply corresponds to scaling this rough geometry up and down the normal of the surface. And this property is a feature, but also a limitation of the model. It's a feature because it let us derive the visible distribution of normals that we use both for importance sampling these models exactly, as well as efficiently evaluating the multiple scattering components that were previously missing from all of these BRDFs. And this was important that it let us go to a very high roughness regime without losing energy. But as we explored this space, we immediately saw that this corresponds physically to an unreasonably spiky geometry where all of the normals of the NDF end up lying in the plane of the surface. And what means if you take a rough diffuse surface and really drive the roughness to a high value, you get these weird dark splotches and the model isn't usable. So around the same time, we proposed that a volumetric representation for these surfaces where the NDF is allowed to extend to the full sphere might be a better way to enter into this high roughness regime, where now we can enter through porous materials, and then in the limit of infinite roughness, this would correspond to floating disconnected particles, where the NDF is just an isotropic function on the sphere. We don't know yet how to efficiently sample the visible distribution of normals for something like a von Mises-Fisher function. So we don't yet know how to evaluate all of these BRDFs. But if we look at the parametric space that this model would represent, we would see here at the top for a specular microfacet, familiar Cook torrents and extended models. At the bottom with a diffuse microfacet, we have the Oren-Nyer and similar models. And you can even blend in between with interface Lambertian facets. But we have this regime where the spiky behavior breaks down. But at the very top corner, we have a model that we do have the BRDF for already. And that is because in 3 dimensions, a sphere with a mirror surface creates isotropic scattering in the far field approximation. And so this corresponds just to Chandrasekhara's BRDF from 1950. And so the ultimate goal of this paper is to compute the BRDF for this corner, where we take Chandrasekhara's model and make this sphere as Lambertian. And so to use a radiative transfer derivation for this, we need to know the right phase function for the particles in the volume, which is the phase function for our Lambertian sphere. It turns out this was solved a long time ago by Lambert himself in his book, where he was studying how much moonlight would reach the surface of Earth from a Lambertian moon, given the phase of that moon, which is exactly why phase functions are called phase functions. This phase function is significantly different from Henny-Greenstein, even at the same mean cosine. It doesn't scatter any light directly forward. And if I render our BRDFs here with both Lambertian sphere and Henny-Greenstein phase functions by using Layer Lab, you can see as I flip back and forth, there's a significant difference. And this is one of the motivations for deriving a new BRDF. We use early results from astrophysical literature that solve something called the albedo problem, which is what we think of as deriving the BRDF. And in this case, the solution will involve multiple h functions, each of which solves a Fredholm integral equation. And I'll have to refer you to the paper for all the details, but we can look at some elements of how the solution works. It starts by noticing that the BRDF is a function of 3 angles, and we can expand this function about the azimuth phi by using a discrete cosine series due to the symmetry of the BRDF. Each function in this expansion is a symmetric function of the 2 cosines, and we can plot these. They look something like this, and they're symmetric about the diagonal in this direction. The top right corner corresponds to each vector lying along the normal of the surface. And so in this top image, a given pixel will correspond to averaging the BRDF around this cone of azimuth phi, and so on. And we notice that the higher order terms get darker and darker. And it turns out that we can approximate the Lambertian sphere phase function using only 3 Legendre polynomials and only have a 0.2% error. And this is great because it lets us draw upon a particular class of solutions for this albedo problem. For a one-term phase function, the solution is very simple. It's the mirror sphere BRDF of Chandrasekhara. It has a single h function, which we can approximate easily. If we move to a 2-term phase function, it gets more complicated. And we see that in a 3-term phase function, we're seeing an exponential explosion in complexity. But this one's just enough that we can actually draw something practical from it. It involves 3 h functions, and in the paper we show how to approximate each of those and the related constants using simpler expressions that are fast to put in a renderer. I'll have to refer you to the paper for more specific details. In particular, one aspect that made this simple was to expand the BRDF, as usual, into 2 components. The single scattering portion we can always evaluate exactly, and then we look at a Fourier expansion of just the multiple scattered part. And if we use Monte Carlo simulation to look at this multiple scattering expansion over a variety of absorption levels, we can see that the bottom term, the second order term, is very dark compared to the rest. And we simplify the derivation by assuming that this is 0. But in the middle row, which is the first order azimuthal component, we do see significant signal in the BRDF. And by approximating this accurately, this is the main difference of our model to previous approximations like Hapke's model. So let's look at some results. Here we compare Lambertian, a rough Orr-Nair model, and Chandrasekhara's mirror sphere BRDF. They all look slightly different, and they have a number of different features. The dusty appearance is probably most similar to the other volumetric model on the bottom row, but with more bright backscattering and more saturated but darker rim lighting. We see the exact same trend in other lighting conditions and objects. Here on the left, more bright backscattering compared to the other models, and again on the right, less bright rim lighting than the other mirror sphere BRDF. I find in particular that on this dragon model, that Lambertian really has a CG appearance in comparison to the more natural dusty look of these models. And flipping to the mirror sphere BRDF again, a more subtle difference, but slightly different coloration and silhouette lighting. To add specular to our BRDF, we can either use Monte Carlo position-free evaluation or the adding doubling layer lab approach. They each have their advantages and disadvantages. The adding doubling solution is faster and lower noise because it computes the layering into a single result and samples it better, but it does require a 2 megabyte pre-computation data set. Comparing to a Lambertian base, we see less difference than in the previous results, but still noticeable as we flip back and forth. So in summary, we've presented a new fast analytic BRDF. You can find the code for it on GitHub. It's fast, easy to use, and offers artists a new set of diffusive behaviors to play around with. Hope you enjoy it, and thanks for listening.
All right, thank you very much for this great presentation. So while the audience can start asking questions in the chat, I have maybe one. You mentioned in your talk and in your paper that you have a fast approximation of this BRDF, and that you computed it using Turing bot. Is that correct? Could you maybe say a bit more about this?
Yeah, exactly. So once I had a fairly accurate analytic model, the set of expressions for it and the performance of it was about 30% slower than the full Oren-Nair result in comparison. So just for real-time applications in particular, I was able to sort of sparsely tabulate the BRDF over angles, 3 angles, and a bunch of absorption levels. And I was playing around with this Turing bot software in the last couple of months and just gave it the single scattering term exactly and a couple other terms that I thought it might be able to use to symbolically find an expression. And it found something that in the end you can sort of subtly see in the paper. There's some comparison images that you can see. They're slightly different, but it's a much more compact result and probably fine for many applications.
All right, thank you. I see that audience has started asking questions. One maybe by Nati Hoffman is, are you planning to try to extend this to interfaced spheres?
So like interface Lambertian on the surface of the material?
I'm not sure what is meant, but I believe so.
Yeah, so when I showed the sort of parametric space of the spherical NDF BRDFs, where you've got sort of a roughness regime that you would imagine a von Mises-Fischer NDF starts to look a lot like Beckman, almost exactly, until it really becomes broad and starts going underneath the sphere. And then so as you move roughness all the way to infinity, you have a bunch of floating spheres, and then you can look at the BRDF as blending from Lambertian to purely specular or something in between. An ultimate long-term goal I would be excited to pursue is to try to find probably a fitted or learned BRDF that would explore that entire space. And so right now we've got things that work on the left from 0 to 1 roughness, and we've got 2 data points in the corners. It'd be really nice to explore that regime in between.
All right, thank you. Yes, there is a question by Lovro Bosnar who asks if it's possible to extend the usage of stochastic geometry to create visible surface textures. He specifies that can the BRDF actually create visible spatial variation instead of resulting in this microscopic invisible surface geometry?
Right. I think I understand the question, and I think it would sort of fall into a class of what I would call glint BRDFs for a rough diffuse surface. So you can imagine that some of the illustrations in the paper where I have a stochastic geometry, there's a scale at which before all the detail is unresolved across pixels and it's completely uniform, you can't really resolve an individual sphere, but you have a sense of noise that doesn't converge away because under a pixel there really isn't enough randomness to average out perfectly to the BRDF. And I think it's an interesting open problem to consider. How do we use Smith's theory and volumetric representations of BRDFs like this to sort of maybe undo one step of the integration, so that essentially these tools could sample this noise at a given scale. So just like yesterday when we saw a BRDF where every part on the surface has some microfacet density, you would also be able to give a model like this the same type of thing, and have some sort of analytics work out what is the histogram of noise levels, color values that you would see given the light and viewing direction and properties of the material. I have no insight to share on that type of problem at the moment, but it's something I find super cool to look into.
Mm-hmm. All right, thanks. Maybe I have a last question when it comes to a new BRDF model. What kind of materials do you expect to have such kind of BRDF behavior?
Yeah, absolutely. So is it possible, can I actually share my screen here? I rendered a couple new results. I will try and see if this works. Or did I just lose audio? I did some renderings in the last couple of days where you can see sort of dusty interiors, bounce light around a Cornell box in a quite surprisingly different way. I thought the BRDF would really only just sort of change the shadow terminator and give a dusty look to these objects. I think given the porous nature of cloth, despite its anisotropy, you might be able to find some distant uses for a BRDF like this, and also some sort of rough rubbers and plastics as well, and definitely for terrain models like rough lunar surfaces and other things. I think you can really get some interesting results, sandy and dusty looking appearances where this obvious backscattering is showing a nice result. Here, this image is just a complete constant color everywhere, and all the colorations coming from the BRDF and that anisotropy in the phase function and second order terms. So these type of applications, I would think. Hopefully that worked.
Mm-hmm. Yeah, we could see it. It was very nice. All right, I think we should move on to the next paper, but thanks again, Eugene. And thank you very much. All right, so our next paper is a collaboration between Alexis Benamira and Suman Patanek from University of Central Florida. It will be presented by Alexis here. Alexis graduated from the Institute of Optics in Paris-Saclay, working with Professor Xavier Granier. And he is currently a PhD student at the University of Central Florida, working under the supervision of Professor Sumanta Patanek. The paper is called the Combined Scattering and Diffraction Model for Elliptical Hair Rendering. And Alexis, you can start when you're ready.
All right. Thank you for the introduction. Oop. Can you see my screen? Nope. Oh, sorry. Let me find out what's going on. Oop. Is it working now? Yep. Yep. Hope you can see my screen. Is it? Oh, sorry. How can I change that? I've prepared it. All right, let me do that again. Fenêtre. J'ai tout l'écran. Écran 2. Here we go. Sorry about the technical difficulty. So thank you for the introduction. Yes, I'm Alexi, and I'm going to present you our paper on a combined scattering and diffraction model for elliptical hair rendering. So I'm going to start by introducing the subject before talking a bit about previous work. Then I'm going to present our model, which can be divided in two parts, a part on ray scattering and another part on wave diffraction. Then I'm going to show some results before concluding. So light has a unique property as it can be considered both as a ray and as a wave. For rendering application, though, we mostly consider light as a ray. As in typical scene, light interacts with objects that are much larger than the visible wavelengths, so their appearance can be very well modeled using ray scattering functions. But there are some exceptions. For example, hair fibers, whose size is comparable to the size of the visible wavelengths. And so for those small objects, modeling their appearance with rays only has some limitation. And in order to fully model their appearance, we need to consider light as a wave. A lot of work has been done on hair rendering, and we're only going to talk about the ones that are relevant to our paper. The first one is one by Marshner et al., where they introduced the first hair rendering model where they represent hair as a dielectric cylinder. Then, based on this model, Dion et al. Offered an energy-conservative hair reflectance model. And based on this work, Xiang et al. Significantly improved the rendering speed as well as the practicability. Closer to our work, in 2017, Conger and al. Offered a precise measurement of hair fiber scattering. And two of the main takeaways of this paper is, first, they show that the hair actual geometry is not circular, it's elliptical. And previous models who attempt to model the ellipticity failed at matching the measurements correctly. The second takeaway of this paper is that during their measurements, they measure strong forward scattering that they're not able to represent using ray simulation only. And in 2020, Xia et al. Offered a full wave model to render, and with this model, they render some new effects that were not taken into account with ray models only. The issue with these two papers is that they offer models which rely on heavy precomputation, which limits practical application. In our work, we offer a practical hybrid model which takes into account the dual natural light, both as a ray and as a wave. Our model is pre-computation-free, and we extend the practical approach of Xiang and al. To extend their model to both ellipticity and wave diffraction. Well, we rely on several assumptions. First, we use the same assumption as previous works, which I'm going to detail in the next slide. And second, we only consider a hair fiber whose thickness is between 50 to 100 micrometers. For other application and smaller fibers, we don't focus on that. So, some background. What happens when a ray of light interacts with the cylinder? Well, we usually say that the scattering function can be divided into lobes, where P here represents the number of time light travels inside the fiber. So for immediate reflection, we have P equals 0, we have a lobe, and after one transmission through the fiber, we have a second lobe P1. We further assume that each lobe can be divided as a product of a longitudinal and an azimuthal function, respectively noted M and N. And this enables to consider the problem in two planes only, the longitudinal plane on the left and the azimuthal plane on the right. And we only focus on the three first lobes, as they account for most of the energy. Our work can be easily extended to further lobes if needs be, but our focus is really the three first one. And in order to take into account the ellipticity as well as diffraction, we can only focus our work on the azimuthal function in the azimuthal plane. So our goal is to redefine the azimuthal function in order to take into account ellipticity as well as diffraction. So let's start on ray scattering. What changes between an elliptical cylinder compared to a circular one? Well, we don't have the same symmetry. For example, the diameter seen by the incident light depends on the azimuthal incident angle. We still decide to use the same logistic distribution as in Xiang et al. Because it's very practical. So what we need to do is to derive the new light transport variable for the elliptical geometry. And what it really comes down to is we need to find phi p for each lobe P, where phi P is the difference between the incident and the reflected azimuthal angle for each lobe. I'm not going to present here the full derivation, but everything can be found in our paper. So now some validation. So to validate the result we obtain, we first did a pre-computed approach, which is a brute force simulation, which is comparable to the approach from Conger and al. And our result is here. So we can see it's very similar, which is what we wanted. So now we apply it to rendering, and this is what we get. On the left side, we have a circular fiber, and on the right side, we have our elliptical model with an ellipticity of 1.5, which is a typical hair ellipticity. And we see that we only have small rendering differences. So this is it for the ray scattering part. Now let's focus on the wave diffraction part. Well, to derive the wave diffraction scattering, we need to make some geometry modification. So initially, we have a wave which arrives on an elliptical hair fibers. We simplify the geometry and consider the fiber as being a rectangular block which stops all light. And now using Babinet's principle, which states that we have the same diffraction figure with a complementary geometry, instead of having a rectangular block which stops all light, we now have a rectangular aperture through which all light goes through and is stopped everywhere else. So now with this new geometry configuration, we can do some derivation. So what we need to do is to calculate the optical path difference. And to do so, we consider a ray of light going through the middle of the aperture and a ray of light going through the side of the aperture at the distance h from the middle. And we calculate the optical path difference between those two rays. We then integrate the electrical field seen by a viewer far away over the full aperture. And we obtain this function, which is a sinus cardinal square. We can see that we have a spectral dependency in lambda here, which is not a problem for spectral renderer, but it is for RGB. So to solve this issue, we decide to perform some numerical spectral integration. And this is what we obtain for the RGB channels. And we can see that they're quite similar for each channel. And they look like sinus cardinal, even though they are not exactly. So we can't do much with them like that. So we need to do some numerical approximation, and we decide to use a logistic distribution. And this is what we get. And SDiff here is the scale of the logistic distribution, which depends on the diameter of the seen by the incident light. And we see that we decide to go for a logistic distribution because it's very practical to use for rendering purposes, even though it smooths out the ripples here. But it still conserves the main appearance characteristic, which is a strong forward scattering. So now let's see the implementation. So as a first part, when a ray arrives on the elliptical hair fibers, we use the ray scattering function using the variables defined earlier. But to ensure energy conservation, we defined a second cylinder around the initial one. And if a ray arrives on the second cylinder without hitting the inner one, then we use a new scattering function, a wave scattering function, using the azimuthal function defined in the previous slide. And for the longitudinal function, we use one from Dion and al. And using this model, we managed to pass the Fernand's test. But by doing so, we introduce a new parameter called DDiff, which we normalize to vary between 0 and 1. For DDiff equals 0, we have no diffraction. And for DDiff equal 1, we have a maximal diffraction. And in this case, the outer cylinder is double the size of the inner one. So now some results. So here, we can see our full model with ellipticity of 1.5 and maximum diffraction. We can see that the strong forward scattering introduced by the diffraction of the light introduced some widening of the hair at the edges of the geometry. And this effect cannot be rendered using rays only. So here we have two images with ray model only, our model with no diffraction and still with ellipticity and a circular cylinder. So we see that even ellipticity cannot account for this strong forward scattering. So some more results. We see on the left the bunny sphere. For a classical circular ray model, we have some hard shadows in the middle of the fur. And using our model, these shadows are considerably softened here. And this because diffractions allows the light to propagate deeper inside the fur, smoothing out the shadows. And on the right, we have kind of the same effect. On the top of the hair here, we can see that the area is quite dark. And we have a sharp contrast in color between the top of the hair and the rest of the geometry. Using our model, we lighten the top of the hair here, and the transition is smoother as well. So now for future works. Well, we first would like to extend our model for smaller fibers for other applications, for example, textile, like silk. We would like to find a better parametrization for our parameter DDIF, and we would like to do some quantitative validation as for now, our validation is mostly qualitative. So to conclude, we have offered a practical hybrid model, which accounts for the dual nature of light, both as a ray and as a wave. Our model is pre-computation free and accounts for both hair ellipticity and diffraction. And we have qualitatively validated our model. Thank you.
All right. Thank you very much for the talk. People applaud.
Sorry for the technical difficulties.
No problem. I'm glad you could figure it out. I could not speak. So thanks to Pascal for stepping in. So maybe while the audience prepares some questions, I had a few. One of them would be maybe what would be required to go to smaller fibers. So the more wave effects would have to be simulated.
So first, the spectral integration would have to be done differently. Here we approximate each channel with the same distribution as they're very close to one another. But if we go for smaller fibers, then the differences between each channel and the differences between each spectral intensities would start to be, the difference would increase, and so approximated by the same function wouldn't be possible anymore. So that would be one thing. And then another thing would probably is that we would need to take into account interferences to fully model the problem. Here we only consider diffraction, but I think interferences would start to play a bigger role, and so it would need to be taken into account.
I see. Okay, thanks. There are a few questions from the audience. One is about performance. What's the rendering performance? And if I can add, what is the difference in computation speed if you put DDIF to 0? Say you don't have an outer cylinder and only simulate the ray interactions.
So in the paper, we present a small table with performances. So yeah, our goal was really to try to be as performant as possible. And so with no diffraction, we only have a slight increase, but it's very, very small. With diffraction, it's a little bit bigger, but it's still a very little overhead compared to, I mean, the reference model was the one by Xiang where they done some really good job on rendering speed. And so, yeah, it's comparable. I mean, it's, for example, I think if I remember correctly, we have some renderings for 15 minutes, it's about a minute difference. So from 15 to 16 minutes, it's really comparable in terms of speed, but it's slightly more.
Mm-hmm. Thank you. Sorry, the question was by Navonil Mukherjee, and we have a question from Nati Hoffman. Does the RGB approximation of the numerical spectral computation preserve color shifting effects from the full spectral model? And or are these effects not very visible anyway?
Yeah, so this effects happens at the border of the main peak, and also for the ripples, that's where it's really striking. And it's true that by approximating, it's mainly by approximating with our logistic distribution, we decide to smooth things out. We only consider this main strong forward scattering. and that's why we cut the maximal diameter to 50 micrometer, because the sinus cardinal function was also a function of the diameter, and so as it decreased, then the difference between the spectral intensity would increase, and so then we would need really to consider this spectral variation in order to represent the full color variation. Here we really wanted to focus our attention really on this main peak, representing the strong forest scattering, which we considered for this range of size as being the main appearance characteristic. But it's true that it is an approximation, and we smooth out those spectral differences that happens on the side.
Mm-hmm. Thanks. There is a question from Eugene Dion, who is asking if you had any results which show a comparison between circular shape with no wave effect, elliptical with no wave, and circular and elliptical with wave.
Oh, I didn't put circular with wave, sorry. I mean, the only one I had was one I showed where we have wave on the left and no waves on the right. And we see that we don't have the forward scattering. No, I didn't do circular wave, sorry.
Okay.
It would definitely be something interesting to see, but I really think it wouldn't change. Especially here, I mean, the ellipticity, the geometry we used was very dark here, so the ellipticity wouldn't change much between circular and elliptical. It really is a wave that has the most striking effect, especially in the configuration where we have a strong light facing the viewer.
Mm-hmm. All right, thanks. And maybe one last question before we move on is from Avijit Ghosh. The diffraction in hair seems to be adding some scattering that would be normally simulated using multiple scattering in hair. Does this mean that with your model, one has to do less work for the multiple scattering component?
No, it's an. I mean, if I understand the question correctly, it's not. I mean, it's not less work. I would say it's more work because we add an extra scattering. Actually, we use in our model we have those two cylinders which are one around the other, and so it's really we use the same number of scattering as in previous model. We just add one if the ray misses the initial fiber by a small amount, which is described by our parameter TDF. If the ray misses by this small amount, then we have to, it's just increase the number of rays that hits actually compared to the classical model where only the rays that actually hit the fiber are scattered. Now we have the rays that slightly misses the fibers that are also scattered. So it actually increases the number of scattering to compute.
All right. Well, thank you very much. I think we need to move on to the next talk.
Thank you.
So yeah, let's thank the speaker again. And so yeah, the next talk was supposed to be practical Ply-Based appearance modeling for knitted fabrics, but the authors had a last-minute issue. So don't hesitate to contact them if you have questions about their work. I'm sure they'll be happy to answer. So we move on to the last paper of the session, which is a collaboration between Télécom Paris and Adobe Research. The authors are Alban Gauthier, Jean-Marc Thierry, and Tammy Boubecker. And Alban will be presenting. He's a PhD student at Télécom Paris under the supervision of Tammy Boubecker and Jean-Marc Thierry. And he's currently doing an internship at Adobe Research in Paris. His research interests include material appearance modeling and real-time rendering. The paper is called MatMorpher, a morphing operator for SVBRDFs. And Alban, it's all yours.
Hi, I'm Alban from Télécom Paris, and I'm going to present our work entitled MatMorpher, a morphing operator for SVBRDFs. BRDF modeling has been widely studied in the field of computer graphics and allows to reproduce a wide range of materials ranging from dielectrics to metals. Now, physically based rendering has become the industry standard for photorealistic materials, since manipulating and editing 2D textures as part of the SVBRDF allows an easy control over the material model. Now let's talk about how to design such materials. One way is to create them using procedural graphs, such as this one, viewed in a material graph editor. This task requires a lot of expertise from artists and can be time-consuming. Another way of designing materials can be achieved using a complex setup to allow for their acquisition. Even if some lightweight acquisition techniques have appeared, they still require the existing material to be present around us to be photographed. There is, however, another way to create new materials when a collection of existing ones is available. That is, through morphing. In this work, we are interested in designing materials by example to explore the space of appearance. Now, many previous work proposed by example design or interpolation of existing assets. Mathusic and colleagues present a texture design framework based on a warping grid and a feature-preserving blending. Their application allows to explore the space of RGB textures by blending between existing inputs. Unfortunately, their technique falls short with high-resolution inputs and only deals with 3 channels per pixel, not SVBRDFs. Some other work address texture interpolation, but are limited to a mask provided prior to the interpolation, as in this work by Ritters and colleagues. The time spent on the processing is not compatible with our need for real-time feedback for the user. Kabul and colleagues propose to optimize for the complete texture metamorphosis under an optical flow framework. Unfortunately, taking into account both matching and blending in the same optimization framework prevents real-time interpolation. Our technique does allow us to obtain real-time complex interpolation behaviors using an editable alpha mask, as we demonstrate here. AppIm by Di Renzo and colleagues allow for the addition of the complete set of SVBRDF textures. They describe linear editing spaces for each of the components of the materials. However, they are restricted by linear combination of channels and are not able to morph one SVBRDF into another. Deep learning techniques are often used to allow nonlinear transformation by navigating through a learned latent space. For materials, Guo and colleagues propose a generative adversarial network to reconstruct SVBRDF from a small set of images. Their method allows for a temporally stable material interpolations, as we can see here, but fails to preserve both input textures during interpolation. To give some details about our framework, we use a typical collection of maps composed of these 5 textures, along with a Cook Torrents BRDF using a GGX normal distribution. We start here by visualizing the result of a naive linear interpolation of each texel in the SVBRDF maps. This method suffers from unwanted overlap of structures, ghosting artifacts, and a lack of sharpness in the output. We propose a pipeline to morph between 2 existing materials, M1 and M2. First, the precomputation part consists in detecting salient features of the materials by extracting contours. These contours are fed to the next part, which computes a transport grid. The grid is then used in real time along with a user-provided blend mask to produce the final SVBRDF. We propose 2 operators which preserve the sharpness of the inputs and allow to produce meaningful geometric information in the output. Let's detail the first part of the pipeline. We use the smooth contour detection algorithm of Krompon von Joey and colleagues to detect meaningful information in the maps. This algorithm works on grayscale images, hence we convert the albedo into a luminous-only channel and keep the z-axis for the normal map. The algorithm produces contours located near sharp features. By default, we extract contours from the height map, which is often sufficient to describe the geometry and produce meaningful contours. Now let's switch to the transport grid computation, which provides a one-to-one correspondence for each texel of both input materials. We sample the contours extracted from the previous stage, and we model a subspace deformation function using a regular grid as coarse deformation structure. We take inspiration from sparse ICP methods and minimize an energy based on the registration of those points. We use a sparsity-inducing norm to remain robust to outliers, along with a regularization energy such as Laplacian minimization and boundary alignment. The optimization produces a transport grid which can be used in the last stage. Now let's detail our histogram preserving blending used in real time. Two successive works by Height and colleagues and Burley studied the synthesis of infinite textures using a randomized texture tiling of a stochastic input, preserving sharpness along the boundaries of each tile. We take inspiration from these methods to preserve the albedo sharpness in our morphing operator. We Gaussianize the distribution of each input, blend them, and then revert the histogram equalization by applying successively the cumulative distribution function of the Gaussian and then the interpolated inverse CDF of the input textures. This method requires a small precomputation for the Gaussianization and can be applied in real time by storing the inverse CDF into lookup tables. Finally, we detail the normal reorientation in our pipeline. We describe the process of material creation for the height map and the normal map to motivate our strategy. A typical artist pipeline for material creation starts with modeling displacement information which corresponds to the base geometry. A coarse normal map can be derived from the height information using simple gradients. Then artists create details to be added on top of the base geometry and save the resulting normal in pre-displacement tangent space. The result of this pipeline consists in the height and normal map provided as part of an SVBRDF. We propose a novel pipeline to reverse engineer this process and blend geometry and details in a consistent fashion. Here is an overview of our pipeline for normal reorientation. We start with the maps of material 1 and 2. We derive coarse normal maps from the height map of each materials using a Sobol operator. Then, we reorient the details present in the original normal maps using a technique similar to reoriented normal mapping described by Stephen Hill and Colin Barré-Brisebois. This allows to recover detail maps which lie in compatible spaces. These detailed maps can be blended using a spherical linear interpolation. Now regarding the height map, they are linearly blended and the result is used to tessellate the mesh. We can compute a coarse normal map from the displaced geometry. Finally, the blended details are added to the normal map, which produces our output normal map. Let's see how our method compares with a simple spherical linear interpolation of normal maps. This is our interpolation, and again. Now let's see some results obtained using our technique. This interpolation is achieved in real time using a uniform blend mask, with an interpolation factor varying from 0 to 1 and vice versa. This is another result of our method with the same technique. Note that more results are available as supplementary materials. Here, we compare our method to the texture design paper of Matuzik and colleagues. Notice how the transport grid fails to precisely match contours between the concrete clover and the lumber tiles. Now we show the results obtained using state-of-the-art deep learning material interpolation compared to their own implementation of a simple linear interpolation on a plane. Notice how the morphing fails to preserve both input materials. If we have a look at the training data used to train the material GAN paper from Guo and colleagues, we notice that some examples result from a linear blend between pairs of materials. This type of data augmentation is not the focus of these works, and they already produce great results for SVBRDF recovery. However, such learning approaches could benefit from a complementary feature-preserving morphing operator to produce novel training data. Now about the limitations of our technique. It struggles with purely stochastic structures such as moss or dirt, as it favors medium to large salient structures. We also assume a rough initial alignment of the two inputs when they are periodic. This could be automated, but then raises the question of how to preserve tileability. Also, our method leads to a simple blend if the metal structures are too far apart. Finally, our method does not exploit self-similarity. To summarize our contribution, we propose an efficient operator to explore and design by interpolation novel SVBRDFs based on an existing collection of materials. We use a transport grid model to guide the morphing process from the dominant metastructures of the materials. And finally, we propose novel real-time detail-preserving mechanisms to blend albedo and normal vectors consistently in this context. The code is available at this link. Thank you.
All right. Thank you very much, Alban, for this nice presentation.
Thanks.
Maybe while the audience writes a question, I have one. You mentioned in the limitation that it doesn't work too well on purely stochastic materials. And that throws a question. Have you considered what would be nice properties for stochastic materials in interpolation over what linear interpolation does? What would be the things to preserve through the interpolation?
So mainly the problem is that the registration between two stochastic heights does not work well. So I would say that using our two other operator for the albedo and normal would help to enhance the interpolation. But this is what fails to the eye when they are like salient metastructures. So in that case, I'm not sure. I guess that as Heights and Burley has shown, like stochastic structures works well when they are blended together. So I guess that not much else. There is nothing that comes to mind, but maybe this can be for future work.
Mm-hmm. All right, thanks. Well, I can ask a bit more. You showed that you can control locally the morphing through some alpha blending operator, and I was wondering what was maybe the use case you envision, or it just it happened to be possible, so why not? Or did you imagine something? So some interface between two materials, for example.
So the idea is to provide better looking transitions between materials, or like the morphing you can imagine, for example, in a movie, if some kind of creature starts from with one form and begins to transform into another, then you want to preserve sharp features in the model. So the model that is enhanced with the displacement and geometric information of the normals. So it's kind of a really generic tool that we provide. It can also help to create and design new materials, as we said. So for example, if you only apply as a channel of one material to another, then you create another material. So I didn't put any example on that, but for example, you can have a concrete material that become a wood material just by changing the albedo and roughness of one into another, and that helps.
Mm-hmm. All right. I think the audience is a bit shy right now. So you showed some comparison with material GAN, for example, and it seemed like the reconstruction from the few pictures was not great in the beginning, so the interpolation was maybe not optimal. But what's your experience? I imagine you have played a bit with it, and what are the properties in which they fail? Don't they preserve the right? Why does it look bad, essentially?
So I think that it works well on like not well-structured materials, but if you use like a well-structured materials, and for the technique, you need to use the inverse optimization to project, to embed the material into the learned latent space. And this is the part that does not preserve the inputs. And so maybe the training set that they have did not like showcase materials with like highly structured materials with like self-similarity. So maybe it's a problem of training sets. But maybe it's also like maybe it's the architecture that does not work so well for material interpolation. This is not the prime intent of their work. It's only a feature. So maybe some other like kind of architecture could help to preserve the inputs and maybe find like a more straightforward path in the latent space. As you've seen, it goes from one form to another, but it's not that straight in the interpolation.
All right, thanks. We have a question from Baptiste Nicolet, who's asking, have you tried other methods for the transport problem? For example, optimal transport plan?
Sure. So good question. So this is the first kind of technique that we tried. Because of course, optimal transport like brings you a nice framework for interpolating distributions. But the problem with optimal transport, it's that it's optimal in the sense that every, like as we explained in the paper, every like mass need to be transported from one distribution to another. And in our case, we have some outliers, some like height distribution that we don't want to display, to move, because like they do not find, like they don't have a destination counterpart. So the idea is to be like kind of robust to the features that can't really blend together. And we have examples where there is like a crease somewhere, and there is not any feature in the other material. And in that case, the crease will just like starts to become like a plane. And in the like context of optimal transport, it would like try to find some mass somewhere and bring it into the crease. So that's why it doesn't work so well with the techniques that we tried.
All right, thanks. Maybe one last question by Juan Raul, who's asking if you could combine this method with some Perlin noise to deal better with stochastic textures. So
yeah, that's a good idea. There is a previous work from like last EGSR that tries to that takes into input, like as input material and some mask, and that uses some kind of stochastic process to extend the material as well as doing some interpolation. So definitely there may be some interesting like research work to try to bring like maybe enhance this paper and like provide better interpolation, maybe a mix of both techniques. But yeah.
All right. Okay, well, thank you very much. Let's thank the speaker again. And that concludes this session. There will be a bit of a break. The next session will start on the time that was planned. So yeah, don't hesitate to chat in the different rooms. All right. Thank you very much, and have a good rest of EGSR.
Okay, hi, hello. Thanks for joining us again after the break to EGSR and to the spectral rendering session. Today we will have two nice papers, both from the Charles University. The first one is called Moment-Based Constraint Spectral Uplifting, which will be presented by Lucia Tovoda. And the second one will be a compact representation for fluorescence spectral data, which will be presented by Chin Hua. And please give a applause for both authors. And I think we are going to start with the first session, which is Moment-Based Constraint Spectral Uplifting by Lucia Tovoda, which is a master student at the Charles University. Like, this paper is the result of her master thesis, and afterwards she will start her PhD at Charles University. Her research interests are in spectral rendering and color science, and now I give the stage to her and to the video.
Hello everyone, my name is Lucia and today I'm going to be talking about moment-based constraint spectral uplifting. To start off, let me take a step back and give a bit of theoretical background to spectral rendering and subsequently to spectral uplifting. In order to simulate light transport in a physically accurate fashion, a renderer must internally represent colors as they are in nature, which is a spectral distribution. By doing so, we are capable of simulating various natural phenomena such as metamerism or fluorescence, and the resulting renders are more realistic. Also, spectral rendering has the additional benefit to predict object appearance under varying illuminating conditions. However, creating attributes for spectral assets, like for example reflectance spectra, is tedious and expensive. It usually requires real-life objects whose physical properties need to be manually measured with a spectrometer, which may be quite impractical. Therefore, as they are a lot easier to create, most of the VFX game engine assets are RGB based, which means that their colors are represented as 3 stimulus values only. To make spectral rendering possible while utilizing these RGB based assets, a conversion from RGB values to their spectral variants is required. This process is called spectral uplifting, or you can find it in other works as spectral upsampling. Because the RGB color space is intrinsically smaller than the gamut of visible colors, different spectral uplifting techniques may produce different results. While all of the uplifts are correct and evaluate to the desired RGB under the illuminant according to which they have been uplifted, in our case this is always the daylight illuminant D65, which is the white point of the sRGB color space, and most of the other RGB spaces as well. However, these uplifts are metamers, which means that under other illuminants, their appearance may change and their color may be distinguished by the human eye. And with the current uplifting technology, we have no control over this behavior, as all the existing uplifting techniques create arbitrary metamers. Here is an example of a render of specific pages of the Mansell Book of Color that is not reproducible with the current technology. Under D65 illuminant, the color gradients on these pages are continuous and smooth. On the other hand, under a spiky, error-prone illuminant, the gradients break down. If we were to, however, use these pages as textures and uplift them with the current state of the art, it has no way of reproducing this kind of behavior. This poses a problem in the VFX industry. There, it is often required to switch between plate footage of real objects and rendered images of their digitized asset counterparts within the same scene. This means that, for example, if you have a superhero movie with a fighting scene, half of the shots may be digitized while the other half may be plate footage. As the viewer must not be aware that an asset switch took place, it is extremely important to eliminate even slight color discrepancies between these two versions. For such work, 3D artists currently carefully model an elaborate double of the real asset and obtain a perfect match under the given illuminant. The problem is that, if the scene illumination changes, this process has to be repeated again. Therefore, for a whole movie, multiple RGB assets of the same object have to be created only due to changing illumination. Our approach offers the possibility to constrain the uplifting process with an input set of RGB to spectrum mappings. During the uplifting, these mappings are preserved, which means that for the input RGB values, the corresponding spectra are always returned. Additionally, in order to allow minor texture changes, RGB colors that are in close vicinity to the constraints uplift to spectral shapes that are similar to those of the input spectra. All the other non-mapped RGB values uplift to plausible, smooth spectra as can be usually found in nature. This extension of standard uplifting systems enables the user to predict object appearance under varying illuminance, which in turn eliminates the repeated fine-tuning work. Our model is based on a simplified version of the uplifting model proposed by Jakob and Hanneke in their 2019 paper, which is currently being used in the art renderer and which was used as a base for the EGSR 2019 paper on uplifting with fluorescence by Jung. It is a cube structure created prior to rendering. The structure is evenly divided into voxels and contains multiple entries in forms of lattice points. Each of the lattice points has an RGB value that corresponds to its coordinate and contains a mapping to a representation over the spectral curve. Specifically, in the original paper, Jakob and Hanneke use a low-dimensional parametric model and are capable of storing the reflectance spectra with only 3 sigmoid coefficients. The sigmoid coefficients are obtained by an optimization tool by minimizing the absolute difference between the RGB of the lattice point and the RGB that the coefficients currently reconstruct for each of the axes. In order to uplift an arbitrary RGB, the original paper proposes finding the voxel that the RGB value falls into, and then interpolating spectra at the corners of this voxel in order to obtain the uplifted spectrum. Our constraint model works in a similar manner, but we also incorporate the user-inputted constraints. As the sigmoid representation is capable of representing smooth and simple spectra only, we utilize a different kind of representation. Specifically, we use the moment-based representation. It was designed in 2015 by Peters, and it has impressive results in representing both smooth and complex reflectance spectral shapes. Although some of the more complex spectra require a lot more than 3 coefficients, we sometimes have to use as much as 20, the results of reconstruction are almost identical to the original input spectrum. So, in our uplifting model, for each of the constraints, we first obtain their moment-based representation. Now, we wish for the RGB values of these constraints to uplift to the constraints perfectly during the voxel interpolation part of the uplifting process. Therefore, all of the corners of the constraints voxels must contain information about the original spectral shape. Therefore, for each of the constraints, we use its coefficients as prior for the optimization process. To preserve the shapes of the reflectance spectra of the constraints, in addition to minimizing the RGB differences, we also minimize the difference between the shape of the original constraint and the curve that the coefficients currently reconstruct. Obviously, as the voxel corners have distinct RGB values, the shapes cannot be identical. What is important is that if you interpolate between them, you get a spectrum that is extremely close to the original one. The rest of the RGB cube is optimized in a similar manner than the method by Jakob and Hanneke, so the non-optimized lattice points use the coefficients of their neighbors as prior for optimization. Also, the minimization functions remain identical to those of Jakob and Hanneke. This is both because we don't necessarily need to preserve the exact shape of the curve anymore, and that using only 3 functions has the additional benefit of better time complexity. During the creation, the cube therefore iteratively grows from the positions of the constraints as shown on the visualizations. For the purposes of these visualizations, we utilized multiple constraint sets in form of color atlases, including a set that had only one constraint in the center of the cube. This approach, which is labeled none, is identical to the simplified cube creation of Jakob and Hanneke, which was, for example, used in the fluorescent uplifting paper. The results of constraint uplifting show very little discrepancies. Even under illuminants such as FL11, which is extremely spiky and error-prone, the average color error between the original and the uplifted spectra is only around delta E of 0.2, which is negligible in terms of human color perception. The only slight discrepancies that the model shows are in the dark colors. The slight sinusoidal-like shapes that can be observed are unfortunately results of the moment-based representation in combination with our optimization process. However, this looks extreme only because the y-axis is scaled and isn't in the 0-1 range, so in reality the differences are less noticeable. Additionally, in the future, we're confident this could be eliminated by case-specific handling. To support our claim, we tested our constraint uplifting model on the pages of the Mansell Book of Color, and we compared our results with the sigmoid-based uplift by Jakob and Hanneke. As constraints, we utilized the individual patches of the pages. The difference images, which are relative to delta E3, clearly show that our approach solves the proposed problem. While there are still some discrepancies in the dark area, most of them are minimal and not perceivable by the human eye. The breaking down of gradients, which is most apparent for the yellow-green pages and which we have already been talking about earlier, is also preserved. We can observe this when comparing the original render with the individual uplifts. Under the D65 illuminant, which is the daylight illuminant according to which all patches have been uplifted, there is no difference between the three renders. Under the fluorescent illuminant, though, we can see that while the sigmoid uplift deviates from the original, our constraint uplift preserves the gradient breakdown almost perfectly. Our method plausibly uplifts the rest of the RGB gamut as well. We tested this by uplifting the same rainbow texture with various cubes constrained with various color atlases under various illuminants. Due to the distinct constraint sets, the uplifts aren't identical, which is to be expected with this method. However, no significant artifacts are visible and the transitions between different color families are smooth. This means that the non-constrained parts of our uplift cubes contain smooth, simple spectra that correctly interpolate. Although the constrained spectral uplifting works as expected, there are multiple limitations to our model. The most evident one is the considerable memory overhead. As the lattice points in the cube are evenly placed, but the constraints do not have to be and generally aren't, it often happens that two constraints fall into the same voxel and therefore one of them cannot be utilized. For example, to see the whole Mansell book of color, which contains only 1,400 entries, we would need a 340-dimensional cube, which is excessive. Therefore, the next step would be to utilize a dynamic structure such as an KD3 or an Oct3, which we leave as future work. The color gamut we are capable of uplifting poses another problem. The uplift cube is an sRGB cube, and our model was designed for the sRGB gamut only. Therefore, it often happens that some of the input constraints fall out of gamut, which in turn means that they cannot be utilized for constraining. Even for the pages of the Mansell book of color that we used as an example, even under the daylight illuminant, we had to eliminate the most saturated constraints. Furthermore, when illuminating the pages with a fluorescent illuminant, even more patches fall out of gamut. This does not mean that the method fails. It just means that the artifacts caused by metamorphism are less pronounced when viewed on a standard sRGB screen. If we were to view these pages on a wide gamut screen, the artifacts would be more visible. However, even then, we would not be able to exactly reproduce the behavior of the pages in real life. For example, if we were to try and reproduce the provided photographs, the sRGB gamut limitations would force us to eliminate some of the most saturated patches in the last one or two columns of the pages, which are the ones that are causing the most evident artifacts. This problem could be partly solved by creating an uplift cube with a wider gamut, which we leave for future work. Other drawbacks and proposals for future work include the already mentioned deficiency in the dark area and performance optimizations, especially during the rendering process.
Yeah, thanks a lot to the authors. Hello, Lucia. And
Hi. Hey, guys.
He's also going to join.
Hi.
Hello. So, yeah, thanks. Was a nice talk. Nice results. So currently there doesn't seem to be any questions. So if anybody in the audience has some questions, feel free to ask them. You can also join in live. So apart from that, then let me start with a simple question. So you mentioned that the rendering overhead is a little bit big. Like, what kind of numbers did you measure there?
Well, this was actually mentioned in the paper, and in comparison to the sigmoid-based uplift, it's about 4 times worse. So that's quite considerable.
Mm-hmm. Okay.
Oh.
Yeah. And
well.
Yeah.
Yeah, and as I said, the memory overhead actually depends on the constraint. So if you have only, for example, three constraints, it isn't excessive, and you can actually use a smaller cube than you were if you were using the sigmoid-based uplift. However, it really depends on the on what kind of on the type of constraints that the user wants to use. So, for example, when I was doing only the green pages, it was excessive because 2 are extremely close, and then the dynamics it isn't a dynamic structure, so it doesn't allow this type of things.
But it's also worth noting that you would only break out this technique if you really need to match the spectral distributions on a real asset. So the memory overhead is the price you pay for getting this sort of capability in the first place, because there is no alternative at the moment. This is the first technique to actually pull this off.
Yeah. And now we have our first question by John Raoul. If you want, you can also ask this question directly live. So maybe he decides. No? Okay. There are some limitations regarding. Are there some limitations regarding the number of constraints and the type?
Yes, the number of constraints is, as we already said, it really depends on the color, the RGB color that they evaluate to. So you can have a lot of constraints if they evaluate to different RGBs, and the type that they have to fall in the sRGB gamut. Once they fall outside the supported color gamut is only sRGB, therefore we cannot utilize them.
So, and another question by Elie Michel. Do you want to have this question live? No. So, would it make sense to use a neural signal encoding, such as Siren or Acorn, to represent your signals?
Alex, would you want to take this one?
Yeah, I think the main issue there is you need to be able to represent the constraints and then interpolate somehow gradually and meaningfully away from them. And of course, some sort of adaptive data structure is going to be used for that in the future. That is future work. And whether we use something deterministic or a neural encoding, that we're going to see that, because all things you can do once you move away from a regular grid have one sort of disadvantage or another. I mean, for instance, if you use KD trees, how do you interpolate in a KD tree? Properties between points. That gets hairy very soon, very nastily. So this falls under the same constraints. Depending on how well this is capable of reliably and smoothly interpolating away from the seed points, it might be worth looking into.
Yeah, so we have around half a minute left. I have one more question. So you were talking that the size grows with the amount of constraints. And I saw that you also work together with Weta and Luca Fascioni. Do you know how many constraints they usually have for when actually in practice?
Well, I'm the one who should answer that, I guess. The thing is, this depends so extremely on the kind of scene that you're dealing with, that the answer is essentially yes, or some other meaningless asterisk. No, because it can be that you have a simple case like some superhero costume with red, yellow, blue, and you need these three colors, and then you have three constraints, bravo. Or it's something more intricate. It really, really depends on the asset.
Okay.
But typically, it's comparatively low numbers, which is why we even bothered doing the grid approach in the first place, because this is already directly useful for those cases where there's a handful of constraints or such.
Okay, yeah, thanks. This is the end of the Q&A session. If the audience has any more questions, please go directly to the authors, and yeah, give them applause. Come on. Okay.
Okay.
Thank you very much.
Thank you.
So this will bring us to the next paper, which is a compact representation of fluorescent spectral data, which is also again by a student from the Charles University, Chin Hua, and Alban Fichet, and again Alex Wilkie. And Xin is a master student or finishes currently her master at the Charles University, and she's interested in light transport, importance sampling, and spectral rendering. And I give her the stage for the presentation.
Hello, everybody. Good morning or good afternoon, depending on your current time zone. I am very pleased to present our work from the historical building of Charles University. Our topic today is the efficient representation of fluorescent spectra. Hope you enjoy. Fluorescent materials are quite common. They have a particular behavior. they radiate received wavelengths to other parts of the spectrum. This means the reflected color is not a shade of the color used to lit the material. On this time lapse, you can see the post-it and the glass reflected received light with a different color than the one used to lit them. The bispectral behavior of fluorescence, we can use a re-radiation matrix. Those matrices represent, for a given radiating wavelength, what is the reflected spectrum. In this basic example, we could measure for each of the frame lit by the monochromatic lights the reflected spectrum of one of the post-its. We end up with this radiation matrix. Now, how do we handle such phenomenon in path tracing? Just let me show a simple example of standard path tracer computing the interreflection between objects in the scene. Each path in the space is bounces through the scene. And in each intersection, we are going to calculate the BRDF. Now, if one of the objects in the scene is fluorescent, the wavelength carried by this ray will be shifted after the reflection. The color of the fluorescent material is shifting to a more saturated color. To present this behavior is the radiation matrix we shown before. In reality, the radiation matrix is a set of measured data. But let's just simplify it as a matrix with numerical numbers. This matrix is huge since it needs to cover the range of visible wavelengths. Each numerical value here means the probability that the wavelength is going to be jumped to another one. Now there comes a problem when used in the radiation matrix. The rendering system is fine when there is only one type of fluorescent material. But what if we have many types of fluorescence in the scene? Even worse, what if our artists want to have a texture with fluorescence, where each pixel contains a different radiation matrix? There will be endless matrices in your memory, thus making the fluorescence not be useful in practice. Our work is trying to solve this problem. Let's review some previous work in the world of fluorescence. Mojic and colleagues proposed in 2018 a method to render fluorescence with hero wavelength spectral sampling and a tracking scheme to render fluorescent media. As we shown before, fluorescence gives us the more saturated color. Young and colleagues use these characteristics to enlarge the color gamut when uplifting. It means they are providing bispectral textures. This requires a large amount of memory because it requires to use radiation matrices for each pixel. With our method, we aim to significantly reduce the memory footprint of such bispectral data. In our method, we are using Gaussian mixture models. These type of representations are widely used in computer graphics. For instance, Voba and colleagues use the Gaussian mixture to accelerate light transport, whereas Hochhorst and colleagues use it for efficient BRDF importance sampling. Gaussian mixture models provide fast evaluation, compact representation, and importance sampling. In our method, we show Gaussian mixture model is also well suited to efficiently represent fluorescence reflectance, while allowing compression and importance sampling. Let's dive into our proposed method for solving this matter. Our pipeline starts with a tabulated radiation data. In previous work, it is fully stored in memory and used directly in the wavelength sampling. We are now focusing on fitting of this radiation cluster. Notice the diagonal is removed here because it is a place where no fluorescent event will occur. Before we fit the data, we filter the high frequency noise under the certain threshold. And then we can perform the expectation maximization on it. But before we perform the EM, we need some modification. Each of our data has one weight. If you divide each element by the integral of the matrix, each will represent as a tabulated PDF. The first option of the modification is to duplicate this data by a large number, and the resulting dataset still has the same portion of weight. Then you can perform the standard EM algorithm on it. But this leads to a huge observation set. Another option is to use a weighted EM, where the preceding training parameters in the algorithm is balanced by the weighting factor. In our pipeline, we will consist with the weighted one. After the fitting step, we have a set of Gaussian mixture parameters that we load into the render. Those parameters will be cut-shot and used for fluorescent events. There are in total 7 elements plus a weighting factor. The first set of parameters is the GMM, which uses 56 bytes for each Gaussian. We experimented that even with small number of Gaussians, it can already has a good performance. The second set of parameters is a weighting factor we use to reconstruct the radiation attenuation. To going from the Gaussian mixture to fluorescent albedo, we will need to apply this weighting factor, and it takes 8 bytes for each fluorescent material. So if we record the full representation of the tabulated radiation, it needs 9,000 bytes for capture in such radiation. This radiation is sampled at 10 nanometer. Let's have a simple illustration on how the wavelength shift is being done on a 2D matrix. If we encounter any fluorescence material, there will be 2 possibilities. The ray is reflected with the same wavelength as the radiating ray. This means there is no fluorescence. In this case, we will sample the diagonal. Or the ray is re-radiated to a different wavelength. This means there is a fluorescent event happening. In this case, we import and sample the radiation. We do this by the conditional Gaussian mixture distribution. We will not dive into the mathematics here, but just to give you some insights on the conditional Gaussian mixture, it's just a slice sampling you can perform on the 2D radiation. By giving the input wavelength, it gives you what is the distribution of your output wavelength. And depending on the sampling path, you can either outshift or inshift. And here is an example of the conditional PDF compared to the yellow fluorescent datasets shown in purple curve. The green curve is the expected distribution of the ray emission wavelengths when the material is radiated at 480 nanometer. Notice the measurement noise present in the original data lowers the highest value of the PDF after normalization. Now let's see some results. Results we are showing is a fluorescent sphere using 3 different datasets: green, pink, and yellow. Now we show you the rendering of the same datasets after being compressed using our method. As you can see, it is hard to see any visual difference. Now, even with a very challenging scene, we get convincing results. Indeed, here each scene is lit by near UV light. This means most of the contribution comes from the fluorescent effect, which is fully approximated by the Gaussian mixture in our method. Even with such challenging case, we barely see the difference. Our method not only provides convincing result, but also drastically reduces the memory footprint. On the left, the raw measurements are used to render the scene. It requires 27 kilobytes, while on the right, we use our method to represent the fluorescence data. Our method uses less than 2% of the memory required by the raw radiation. The memory difference is even larger with fluorescent texture. This texture is 32 by 32. Among those pixels, we have 255 fluorescent ones. The raw representation needs 258 megabytes for both spectral and bispectral pixels, while our methods only require 4 megabytes for this texture. If you increase the resolution of the texture, the ratio is getting even bigger. This means our method makes the usage of bispectral texture practical. Finally, we will address some feature work. So, in conclusion, our method is memory efficient and allows fast evolution and important sampling. It also provides convincing results even with challenging illumination. However, in future work, we would like to explore different families of functions, possibly with positive skewness to have better representation for our original data. Also, we describe in the paper 2 strategies to improve visual appearance by rescaling the GMM. Further work will be done in this direction. We hope this presentation will encourage our community to provide new measurement data for fluorescent materials. As a matter of fact, we were limited to a very restricted sample set of measurements to evaluate this work. Having access to a larger set of measurements would benefit future works for efficient representation of bispectral materials. Thank you very much for your attention. We made the implementation of this paper open sourced. You can find it following this link here. We rely on art for all of the rendering results. If you have any questions, we will be very pleased to answer.
Yes. Thank you very much, Xin. Let the audience give you applause. Yes, this
Hi.
was... Hi. So there's also Ivan, who's gone and who's back, and Alex again. So yeah, thank you for your talk. This looks like a massive memory reduction, and also the results look quite nice. That's pretty cool. So as you mentioned, if there is somebody from industry out there who has some measurement data, please give it to these guys so they can continue work. Or if you know anybody who has some of these data, yeah, feel free to contact them, I would say. So you mentioned you only had some limited amount of test data. Like, where did you get this data from?
It is from LabSphere, so it is one open source company, if I remember correctly. So they provide some like very limited full radiation matrix measurement.
Well, the thing is, we probably Alex will have more insight about it because it's part of the art source code, like an asset of the thing. But I'm not sure if it's even available now from the LabSphere website. So if you want to have access to those data, I would say, yeah, grab it from download art. It will be there.
Download art and get it from there, because I was given this data. This was never publicly available from there, but they were the only ones with for a while who really did measurements for the pigment industry. I mean, this data set is 20 years old. It would be high time that somebody did a more noise-free measurement of the stronger fluorescent pigments you also get out there. So yeah, it's an old data set, but it served its purpose there.
Yeah, so at least if you ever thought about making data sets and stopped doing it because you had no idea how to render it, at least now you can render it. So this should not stop you from now doing the data sets.
Yeah, it's a chicken and egg problem. We've now taken care of the chicken. Now somebody needs to bring eggs.
Yeah, exactly.
Cool. Yeah, so back to the audience, please. If you have any questions, feel free to ask. I have one, like, so you used EM for fitting your Gaussian mixture models. So have you also considered other optimization techniques for that? Because like EM only optimizes for the maximum log likelihood. So have you tried to do anything else?
Yes, we are also considering to add, for example, a map version of the EM algorithm. But I think the main points of improve this method will be to see if we have we can add some screwness Gaussian to it, and if we have more data sets, we can try on other like mixture distributions.
Oh yeah, finally some questions. One from Alisa. Alisa, do you want to give the question directly, or then you just need to click on the upper left? Oh, okay, she doesn't have camera. So the question from Alisa, how do you handle the non-fluorescence diagonal of the re-radiation matrix? Do you store the diagonal explicitly, or do you also fit a 1D or 2D Gaussian to it?
We store it directly, so the fitting is only made to the cluster of the radiation. There is no fitting on the diagonal.
Mm-hmm. Okay, and another question from Navuli. For your implementation, did you use the hero wavelength method as well?
Yes, our method works directly in the hero wavelength sampling, and in our paper we have actually the pseudocode how to plug in it into the hero wavelength sampling. So you can check out.
Okay, thank you for answering. Are there any more questions from the audience? No? So I think we are also almost at the limit of the Q&A session. So I would say let's give the authors of both talks another applause from the audience, please. You can do better. Okay. Oh, there's another question. We still have half a minute. Are there special properties for the re-radiation matrix?
I can take this one if you want.
Yeah.
Well, the thing is, and that was the catch of the work, basically we have only 3 datasets. So that's something that would be very interesting to dig, right? But based on these 3 datasets, it's hard to propose something much more specific to fluorescent data. Oh, Alex.
But something that's worth noting is, I mean, we have measured data sets of these 3, but based on, you can read the rough structure of the re-radiation matrix from other data that's available. You get these Stokes shift plots for industrial fluorophores that you can buy, and they all seem to have, give or take, the same sort of structure in their re-radiation matrix. We have not seen anything where the structure is fundamentally different. See also the 2019 paper by Elisa. Hi to Elisa, by the way. The fluorophores behave vaguely similar, so we reckon it would work pretty much on any real fluorophore you can drag out.
And like having the positive skewness stuff, probably, I mean, that's a kind of a guess, which probably is really good for a lot of fluorescent data because they have all that kind of positive skewness to the radiation part.
Okay, thank you. So we are now at the limit. Thank you very much. And for the audience, in 10 minutes, we will continue with faces and body. So after a small break, join back in.
Bye-bye.
Bye.
Bye.
All right. Hello, everyone. Welcome to the last session of EGSR. This session is about face and body. So the first paper is called Deep Portrait Lighting Enhancement with 3D Guidance. The authors are Han Fangzhou, Wang Kan, Du Hao, and Liao Jing. And Han Fangzhou will be presenting the paper. Let's welcome him.
Hello everyone, here I'm going to present our work, Portrait Lighting Enhancement with 3D Guidance. This is a work done by City University of Hong Kong and supported by Huawei Ascend. In this work, we enhanced the lighting of a portrait image from a bad lighting with dark shadows, blurry details, and maybe high ISO noises to an enhanced lighting with more pleasing shading effects without blurry or noisy artifacts. To do this, we reconstruct a 3D face model from the input image and predict a group of enhanced lighting parameters to render the face model. The rendered image is used to guide the image-to-image translation network for generating a more photorealistic and lighting-enhanced image. Traditionally, lighting enhancement tasks, no matter for general images or for portrait images, are performed on the 2D image level. This makes it difficult to distinguish different lighting conditions, as well as to model the geometry. Meanwhile, as face geometry is very delicate, lack of fidelity in results is highly noticeable. This requires the method to effectively model the interaction between lights and the face geometry. Moving this question into 3D space, we can reconstruct the geometry and albedo of the input with 3D MM. With the geometry and light model, we can simulate realistic shading effects, while the albedo can provide extra texture information to help recover the shadow regions. As the reconstruction and rendering process will lead to unavoidable distortion, we do not directly use the rendered results as our final output. Instead, we use it as the guidance to condition the generation process of the final result. Based on this idea, we propose a two-stage framework, which includes a lighting correction stage and an image enhancement stage. By exploiting 3D facial information, the method outperforms previous 2D approaches. Another contribution of this work is the image enhancement stage, uses a transformer-based image-to-image translation network that models long-range correlations between the guidance image and the input image. Meanwhile, we propose an efficient data synthesis method that can produce photorealistic training pairs for this task, along with a synthetic dataset. To introduce our method, I'll start with the first stage of the framework. The first lighting correction stage takes the input image and disentangles its shape, albedo, and pose with 3D MM. Meanwhile, a lighting parameter estimation network estimates the input lighting parameter and predicts the lighting parameter difference, which indicates the mapping distance from a bad lighting distribution to an enhanced lighting distribution. And the guidance image is rendered with enhancement lighting parameter and the reconstruction results. To train the lighting parameter estimation network, the rendering pipeline needs to be differentiable. Here, we use the soft res to replace the rasterization and hidden face removal with a differentiable aggregation function. Meanwhile, instead directly predict corrected lighting parameters, we adopt a bi-branch design and output the input lighting parameters and parameter difference. By separately compute loss with the input image and the label image, the network can learn to estimate input lighting as well as map the input lighting to its correction target. In the second image enhancement stage, we use an image-to-image translation network to make use of the guidance image and generate visually pleasing results. The network takes the input image and the guidance image into an encoder with several transformer blocks, and outputs the feature to a decoder with multi-speed blocks. There are 3 loss functions used in training the enhancement network. We use adversary loss to minimize the distribution distance between the ground truth and the output. To stabilize the training process, we also adopt a feature matching loss between different layer features extracted by the discriminator of the real and the fake images. A perception loss is also used to further guarantee the result quality. Now let us get a little deeper to the transformer block. The traditional transformer captures self-correlations by calculating Q, K, V using the input feature. But we want to model the relations between the input and the guidance. Therefore, in the proposed block, the input feature is extracted from the input image and the guidance will first be warped into the same dimension as the input feature. Then Q is calculated from the warped feature, while K and V are calculated from the input feature. To the best of our knowledge, currently there exists no high-resolution phase light enhancement datasets. To build such a dataset, we first ask volunteers to manually select a group of portrait images that are believed to have good lightings from FFHQ dataset. This group of images forms the enhanced lighting distribution as shown in the blue oval. They will be used as a ground truth for training to guarantee the outputs to be more natural than using synthetic data. The corresponding input images are degraded from target images. Specifically, we first estimate SH parameters for all target images and calculate their mean value. Given the SH parameters of one target image, we randomly sample an ideal SH parameter within a small radius of the mean and extrapolate away from the parameter of the target image to get the degraded lighting. With degraded lighting parameters, we can generate the degraded image. After degradation, to make the synthetic data as realistic as possible, a blurring filter is applied to the degraded image, followed by a Gaussian noise to simulate detail loss and noise artifacts in poorly relit images. To further prevent unrealistic synthetic images, volunteers are asked to perform manual filtering, after which 6,828 out of 20,000 image pairs are selected to form the final dataset. Training with the dataset, networks will learn to adjust the lighting of the input images towards the elected standard, yet the results will still preserve the lighting characteristic of the input images, instead of undesirably mapping all lighting conditions to a normalized one. To evaluate our method, we have tested on both synthetic data and real data. Here we show some examples of results on synthetic data. From the images, we can see that the lighting conditions are improved, while still preserve the original lighting characteristics of the input images. Besides, both types of regions with dark shadows and highlights are recovered. We also compare our method with state-of-the-art lighting enhancement methods, like Enlighting GAN and Zero DCE, and portrait relighting methods, such as DSIPR and SMFR. In terms of very dark areas, all of the compression method cannot produce desired results. Enlighting GAN and Zero DCE achieve better results than the relighting methods, but they still perform badly in generating natural face textures and pleasing lighting conditions compared to ours. This proves the superiority of the proposed method in making use of the 3D information and the correlations between the 3D guidance and the input. We also test our method on real images. although the domain gap between synthetic data and real data is inevitable. The testing results on real images demonstrate that our synthetic dataset enables networks to generalize well on real poly-related images. As there is no ground truth for the enhancement of in the wild images. We also conduct a user study to perform numerical evaluation among our method and the related works, where our method is ranked in the first place. To extend our method to handle images with random face size and location, we train an image harmonization network to adjust the brightness of the background according to the enhanced face region. We compare our harmonized enhancement results with the input and the enhancement results directly padded to the original background. It can be seen that the discontinuity on the background or the hair region of the images after the enhancement is smoothed by the harmonization network, which effectively enriches the working scenarios of our method. Although it is proved that the lighting guidance is useful, and more accurate and realistic guidance will lead to better enhancement performance. A limitation of current method is that it is unable to alter the lighting attributes such as direction or strength of the enhancement results with simply modifying the lighting guidance. In the future work, the framework can be modified to perform relighting function with generating multiple guidance target pairs for one input image. Another potential limitation is because a limited number of SH coefficients are used. The synthesized training pairs cannot represent all kinds of illuminations. Thus, our network may not be able to handle this challenging illumination perfectly. This is a common problem for all lighting enhancements and relighting methods with synthetic training data, and future work can be done to further reduce the domain gap. Thank you for listening.
All right. So the audience, if you have any questions, you can type in the question box, and you can also click the button so you can ask your questions. So while the audience are still typing, I can have my first questions. So first of all, very good work. Congratulations. I believe there will be a lot of applications for this kind of work. And I see that your method is using the FFHQ and using that as a kind of guidance as a good quality lighting, right? So my question is that do you assume that all the images in the FFHQ dataset are equally good, or there are still some better and some bad?
As we said in the paper, we hire a group of volunteers to select some images from FFHQ, which they think that they are with acceptable or satisfactory standard of lighting. Yes, we don't think all of them is good. Yeah.
Okay. And so, in terms of improving the lighting quality, actually, is there a way to measure the quality of or improvement because the light you are not based on a physical based lighting model, so that we cannot to accurately measure or compare the different light. So instead, aside from your study, do you have any more subjective method to measure the quality of the lighting?
You mean that if we have a method to measure the how good is the lighting is, right? For a group of images, we no, actually, for our user study, we only do comparison between different methods like ours and some other methods. Yeah, and to control the standard of lighting, we mainly based on the selection of our volunteers. So their election standard represents our understanding or our definition of good lighting.
All right. So there's a question from the audience. So did you try to ablation study regarding to the transformer block?
Yes. So we have presented that part of result in the paper. Yes, we have ablate basic every key ideas of our network. Yes, including the transformer block.
All right. So could you give us a high-level conclusions of what the transformer block will affect the result?
Yes, sure. So the reason we use the transformer block is that we want to model a relation between our guidance image and the input image with backlighting. And we find, as we can see from the ablation results of the transformer block, there are some areas of the input images, especially those areas with very dark lighting or very low value of pixels. They cannot be recovered very well. Yes, because they do not have a relation like to decide that which part is related to the guidance image that is is to suggest what they look like when there is a better lighting condition.
All right. So since there's no more questions, I may ask the final questions. And
yeah,
so, do you assume that the input image is well exposed, or you still can correct like exposures and the white balance issues of the whole image? I mean.
I'm sorry, I didn't hear you quite clearly.
Do you assume the input image is already well exposed, or there are maybe some underexposure or overexposure images? You still can. Those are still regarded as bad lighting.
Yes. For our method, we actually use the synthetic method to build a group of input images, and they are like degraded from the selected original FFHQ images as the bad lighting conditions. Yes.
All right. So maybe due to time limit, I think that's all for the session. And let me thank you again, and another round of applause. Thank the speakers.
Thank you.
So the next paper, yes. Next paper is called NeLF, a neural light transfer field for portrait view synthesis and relighting. The authors are Sun Tiancheng, Lin Kaian, Xu Zexiang, Li Sai, and Ravi Ramavusi. Sun Tiancheng will presenting for this paper.
Can everyone hear me? Okay, nice. So I'll get started. So hello, everyone. Welcome to our talk. This is Tiancheng Sun from UC San Diego. And today I'm going to introduce our recent research, which we called NeLF, Neural Light Transport Field, which enables simultaneous view synthesis and relighting on human portraits. So let's get started. So digitalizing human portraits is a long-standing graphics and vision problem with many applications like computational photography and video conferencing. And in recent years, there has been a lot of advances on this topic. The Digital Emily project showed us the possibility to create a digital person that is almost indistinguishable from real photos. And the coded avatar proposed by Facebook enabled people to talk with each other virtually through VR devices. However, these techniques usually require sophisticated hardware setup such as light stage or involves complicated and time-consuming optimization process. And in this work, we try to find a practical and efficient way to digitalize human portraits from natural portrait images and resynthesizing novel images under new lighting and viewpoints. Recently, NeLF have initiated significant progress in photorealistic view synthesis. Various radiance field extensions have been presented, and some concurrent work also aimed to address problems in human portrait capture. So John has already gave a very great keynote in Wednesday on NeLF. And the basic idea of NeLF is to implicitly represent a scene as a volumetric field encoded in a simple MLP network. Such kind of representation makes the rendering process straightforward and also leads to a trivial auto-integration. Auto-differentiation. And in this way, we only need to supervise the rendered image and rely on the end-to-end training to figure out the geometry and reflectance. So the volumetric model leads to great improvement on the performance of view synthesis. However, most NeLF models have the lighting baked into its representation, which means it is not possible to change its lighting condition. And in addition, most NeLF models need to overfit to a specific scene using a large number of images in order to get good results. A recent extension, NeLF, added lighting into consideration, but still it requires densely captured images as input, and it requires a time-consuming per-scene optimization in order to get good results. So in this work, we aimed at a practical solution for portrait view synthesis and relighting using a NeLF-like volumetric representation. Our goal is to use only the portraits sparsely captured from casual setups as the input images, and build a system that does not need overfitting and can generalize to unseen portraits. Let's first review the previous methods that are most relevant to this work. In SIGGRAPH 2019, we have presented single image portrait relighting. We have shown that it is possible to infer lighting information and perform relighting with only a single portrait or a sparse set of portraits. However, this work on portrait relighting focuses on changing only the lighting and is not capable of handling view changes. On the other hand, recently there emerges some work that try to make NeLF generalizable to novel scenes. In the paper IBRNet, the authors propose to first use a convolutional neural network to extract features from input images, and then construct a volumetric representation of the scene using the projected image features. In this way, they can train the network on various scenes and adapt to novel scenes during testing. Although it still requires fine-tuning in order to get state-of-the-art performance, the results without fine-tuning are already reasonable. In this work, we utilize a similar idea to tackle the problem of simultaneous view synthesis and relighting. Now let me introduce our proposed method. Our system takes as input a small set of 5 images of a human face, which are captured roughly from the frontal view. We assume the captured portraits are lit by the same distant light, which can be modeled by an environment map. Then, we apply a UNet-style convolutional neural network to the images in order to extract the original lighting and compute the image features for each image. We use the extracted image features to construct a volumetric field of the captured subject. And then, when we view the subject from a new view, we sample points along the ray and use a shared MLP to compute their density and radiance. Notice that here, the predicted radiance at each 3D point is dependent on the target lighting. Using the radiance under the new lighting, we integrate the radiance along the ray and render out the final image. This is the whole pipeline of our algorithm. The kernel of our method is how to predict a radiance, big L, which is dependent on the target lighting, a small l, at each 3D point. And here, the concept of light transport. The light transport T is a vector whose dot product with the target lighting environment map produces the outgoing radiance at the 3D point. And according to the rendering equation, such vector is well defined and can encapsulate all the complex transport from the light source to the 3D point. We predict the light transport vector for each 3D point in the volume, which enables us to perform relighting on captured portrait using the volumetric representation. While we can directly predict the light transport vector, this can easily lead to the network memorizing the portrait appearance in the training set. Thus, rather than directly predicting the light transport vector t, we propose to predict the scales relative to the observed pixel colors. The predicted scale t prime have the same dimension as the light transport t, and compute the light transport vector by multiplying the observed pixel color I from the input images. And as we will show in the ablation study, this design effectively retains the highest information in the original input image and enables better generalizability of our network to unseen real portraits. We train our network on synthetically rendered human face data. This data does not model the distribution of the real human faces very well. Thus, naively training our network using rendered faces results in poor generalization on real portraits. It is optimal to include new real multi-view portraits in our training data. However, there is no publicly available large-scale human face dataset, and it's also challenging to capture real portraits under different viewpoints and lighting. To this end, we propose a novel domain adaptation module that effectively enhances the generalizability of our network. We augment the CNN feature extractor with real portrait images from the Celebrity A dataset. However, these real images do not have ground truth labels of their lighting or camera parameters, so we cannot train them end-to-end. However, we can feed them into the CNN and ask the CNN to recreate the original image. In this way, we can help the feature extractor to reason about real portrait images and avoid overfitting to the biased distribution of the synthetic portrait dataset. We train our network on 20,000 synthetically rendered human portraits and 30,000 real portraits. The training images have the size of 512, and we represent all the lighting as 8x16 environment maps. This is also the size of all the predicted light transport vector. Our network converges after 300,000 training steps, which takes roughly 36 hours. The training loss we use composed of several parts. First, similar to previous NeLF paper, we directly supervise the rendered images using an L1 loss. Also, since we are mainly trained on synthetic data, we also supervise the predicted depths and the alpha channels. We also supervise the prediction of the original lighting using a log L1 loss. And finally, we also have a self-reconstruction loss on the real portraits we use for domain adaptation. To the best of our knowledge, we're the first to achieve simultaneous view synthesis and relighting on unseen subjects from a sparse set of multi-view images under natural illumination. Our previous work, single image portrait relighting, can change the illumination of single image, while IBRNet achieves view synthesis on novel scenes. We use a combination of these two state-of-the-art algorithms as a baseline. There are two possible ways to combine: first relighting and then view synthesis, or first synthesize new view and then change the lighting. So here we show the comparison result. We observed that the baseline methods often leads to obvious visual artifacts in their rendering. Our approach instead can achieve much higher visual quality, constantly producing realistic rendering across different lighting and viewpoints. These two baselines fail for different reasons. If we first relight the input images, the relighting algorithm might perform slightly different on each input view, which will break the multi-view consistency for view synthesis. On the other hand, doing relighting after the view synthesis also does not work well, since the relighting algorithm now has no access to the multi-view information. And in contrast, our approach learns to effectively aggregate multi-view appearance feature to predict the light transport for each shading point, leading to accurate relighting effects that are consistent across multiple views. We also study the effect of input view numbers on the rendering quality. Our network is originally trained with 5 images as an input view, and we test our network by feeding different views in a different number of views into the network for view synthesis and relighting. This is a ground truth, and here are the results with different input views. Our network fails to render meaningful content when only 2 images are given. However, as we have 3 or more images as the input view, our network can render new views under new lighting with decent quality. Now we show the results of real captured portraits and compare them with the ablation method. We first ablate our algorithm by directly predicting the light transport rather than modulating the prediction using pixel values. This will lead to blurry results without detail on the portraits. In addition, the method introduces more color shift compared to our full algorithm. We also show the effect of our domain adaptation module. With additional adaptation module, our network is able to generalize to unseen color distributions. Without the adaptation, the network fails to recreate the vibrancy of the input image. Our domain adaptation module essentially regularizes the image feature extractor to be able to better reproduce appearance in the original input image. So in this talk, we introduce neural light transfer field, which enables simultaneous view synthesis and relighting. We demonstrated that with only 5 portraits captured in a casual setup, our method is able to generalize across unseen portraits and produce better portrait rendering than previous approaches built specifically for either view synthesis and relighting. The key point is to predict the light transfer vector at each 3D point in a volumetric representation, and we also introduced a domain adaptation technique in order to work well for real portraits. Our approach is not without limitation. Since we are trained on synthetic dataset, our model might exhibit some color shift in certain cases. Additionally, the specular components of our portraits are manually added and does not accurately model the reflectance of human skin. So the results might look a little bit diffuse. Also, in our paper, we use an 8x16 environment map to represent a light transfer vector. It is effective, but may be insufficient in some difficult cases. How to accurately and efficiently represent the light transport vector still remains an open problem. And at last, I would like to thank the following people and group for supporting this paper, and thank you everyone for attention.
All right. Very nice work. So we already have questions. So the first question is about how the input light is predicted. What inputs are required to predict input light?
So we are predicting the input lighting using the input images, right? We have 5 input images from different views, and we use a convolutional neural network and to predict the lighting for each view, and then we merge them together and to get a consistent global lighting prediction.
All right. So the second question is that it is essential to estimate the camera pose for the input file portrait as a NeLF does.
Correct. We need the ground truth camera pose in order to perform this whole procedure. So we already know the position of the cameras.
All right. So yeah. The next question is about for the self-reconstruction task, was there any specific reasons to choose Celebrity HQ instead of FHQ?
There's no specific reason. We just found that Celebrity A. We actually use Celebrity A masked dataset where we mask out the background. We found that this is quite important in our method because we're doing view synthesis and we cannot really synthesize the background movement.
Okay, so the next question is, it appears that all the portraits has their hair hidden. So with this, because those details are not reconstructed by the network?
So I think what you're referring to is the synthetic data set. So unfortunately, the synthetic data set was from the public data called Facescape. They provide meshes which does not contain the hair. And I think we showed in our real results that we can work well on real photos with hair.
All right, so due to time limit, I think this is the last question. Did you evaluate your method with light stage data?
Oh, so at that time, I lose access to the light stage data, so I didn't have tried that. Yeah, but I believe with the light stage data, with abundant light stage data, we can train a better network.
All right, so I think due to time limit, I think we need to cut the QA session for now. So we need to go for the next paper, but still Ken Chang. The next paper is human hair inverse rendering using multi-view photometric data. The authors are Sun Tiancheng, Jiu Nan, Carlos Alija, Crispy Henry, and Ravi Ramamurthy. And Sun Tiancheng will continue to present us the paper.
Hello again, everyone. This is Chen Sun from UC San Diego. So in this talk, I'm going to focus on the most difficult part of our face, human hair. And we develop an inverse rendering algorithm for human hair using multi-view photometric data. So this is a work that we collaborated with the Facebook Reality Lab. So with the recent advances in appearance modeling, nowadays we can create super realistic human models that is indistinguishable from captured images. So the left image is a render result of one of our human models, and the right one is a captured one. Although there still contain some subtle differences, overall the render image is very similar to the captured one. However, as one might notice, there is a hairband in the captured image, which is used to make the hair to stay away from the forehead. And this actually leads to one key problem of human modeling. Face and hair are modeled in two totally different ways. Modeling human faces is nowadays not a very difficult problem, but modeling hair still remains a big challenge. So for human faces, nowadays we can easily reconstruct the detailed geometry and texture from several captured images. However, the hair part is still hand modeled by artists. Moreover, the reflectance property of the hair strands is hard to infer, and artists have to fine-tune the parameters in order to match the captured image. So the process of creating hair model is much more complicated compared to face modeling. So in this paper, we aim to fully automate this procedure. So formally speaking, we want to build a full hair inverse rendering system that is practical and can reconstruct human hair realistically. It takes as input some captured human hair images and infer both the hair geometry and the reflectance property. So in order to achieve this, we use a light stage to capture the data. So the light stage is a device which consists of hundreds of LEDs, and we can programmatically control the on and off of the lights and capture the image using cameras. So to formally define our problem, the input images is captured from known cameras under known light patterns, and the output should be the shape and the reflectance of thousands of hair fibers, which represent human hair. So unfortunately, due to pandemic, we don't have access to a well-maintained light stage. So instead, we used to render realistic images using Blender, and we built a virtual light stage environment inside Blender and use rendered human images as the input. So before we jump into the project detail, let's first see what happened done in the past. So the most relevant work in hair reconstruction is a paper from Facebook Pittsburgh team in SVBRDF 2019. They had a similar setup as us. They captured the images of human hair using 70 cameras under uniform lighting and developed a line-based multi-view stereo for hair. So traditionally, we assume the scene is constructed of planes with normals. And here in this paper, they propose to use a 3D position and a 3D line direction to represent the hair. This paper gives strand-level accurate reconstruction, and artwork is built based on this paper. So although our papers seem similar to the previous work, we solve different problems under two different setups. We both use the cameras installed on a sphere, but we are using fewer cameras than theirs. Also, the captured hair images in Nams et al. Work are all under uniform lighting, while our inputs are captured under multiple, to be specific, 36 plots. And with the lighting variation in the input image in our paper, we aim to not only reconstruct the hair geometry, but also hair reflectance. And this enables us to render out the hair image, and it should be similar to the captured image. So here is an overview. The input of our framework is multi-view photometric data. In other words, a set of images taken from various viewpoints and different lighting conditions. So thanks to the realistic face and hair models created by artists, the rendered human is almost indistinguishable from real capture. We place 24 cameras and 36 point lights towards the subjects, and we also assume that each camera has a co-located light source. And given 24 times 36 images captured from all cameras under each lighting source, we first reconstruct the dense set of hair strands using the theory of multi-view photometric stereo, and then estimate the reflectance property of the hair strand using the infrared geometry. So we can reconstruct the hair geometry in multiple steps. First, we extract the 2D orientation from the capture image. And using these 2D orientation maps, perform a stereo matching algorithm and reconstruct a set of 3D line segments. And finally, we connect and extend these short line segments into long hair strands to get final geometry. The first step is to detect the 2D hair orientation from images. We use a log-Garber filter to extract the hair orientation. We convolve the image with these filter banks, each representing a specific hair direction. And the maximum response will occur when the hair direction aligns with the filter direction. We found that log-Garber filter is more effective than line detection than Garber filter, which was widely used in the literature. So please refer to the paper for more detail. So besides a 2D orientation map, we also compute a confidence map depending on the peak value of the filter response. The confidence map denotes how likely a pixel corresponds to a hair strand. So recall that for each camera, we have multiple images taken from different point lights. We extract the 2D orientation and confidence from each photometric images, and then use a weighted average to merge them into a final 2D orientation and confidence map. So in the rest of the algorithm, we will only use a merged line orientation and confidence in the right. So the next step is to reconstruct 3D line segments. In other words, given the captured images and the 2D line orientation, extracted from each camera, we want to get the line segment in 3D. The key to reconstruct the 3D line from 2D orientation is to find the correspondence between cameras. For example, if we know the red pixel and the two white pixels are looking at the same 3D point, we can simply connect the camera origin and their pixels, and the intersection point should be the 3D location of the 3D point. So here the goal is to find the correspondence of 2D line segments between cameras. We follow the previous work, where we model each 3D line segments with its 3D line position XYZ and its 3D line direction, which is represented by a 3D normalized vector. So outline of our algorithm is as follows. For each pixel in each camera, we first find the neighboring camera which might look at the same point. Notice that this is not finding the correspondence between pixels, but just find the correct cameras that used to find the matching pixels. Also, notice that this is computed pixel-wise, which means each pixel might have different camera candidates. And the second step is the core step in our algorithm, which is to find the optimal line segment of this pixel given valid neighboring cameras. So the first step is to find neighboring cameras, which might look at the same 3D point. Given the pixel position in the camera in our setup, we not only have multiple cameras, but also have multiple lights. So suppose we have a point light source B, which is very close, to the original origin of camera B. And if we examine the image taken from the camera A under lighting B, then the image intensity of the red pixel should be non-zero, which means camera B contains a line segment that the red pixel is looking at. And conversely, for C, if there's an occluder between them, then if we examine the image taken from camera A under lighting C, the intensity should be 0 because it is occluded. So this means that the line segment at the red pixel is pointing at the position that is not visible to camera C. So we can simply eliminate it from the valid camera list. In practice, we place a point light next to each camera and use the interchangeability of camera rays and light ray to get the visibility information for each pixel. The next step is to exactly compute the line segment that the pixel is looking at. More specifically, we have to find the depth D and the 3D line direction L. One key observation we have is that we can solve the optimal 3D line direction L if the depth D is given. Suppose we know the correct depth D, we can first compute the 3D position of the line by following the vector from the camera origin to the red pixel. Notice that the small red line segment on the image plane is actually the projection of the blue line segment in 3D. And we already know the red line segment from the 2D line orientation map. So in order to let these two lines consistent with each other, the blue line should lie inside the plane formed by these two yellow lines. The line in the image plane and the vector from camera origin to the pixel. In other words, the vector L should be perpendicular to the cross product of these two vectors. So mathematically, n dot L should equal to 0. Next, since we have the 3D location of the line segments, we can project the 3D point to all valid cameras and find the 2D line segment from the corresponding 2D orientation maps. And similarly, L should also be perpendicular to the normal vector n in all the cameras. And this constraint can be formulated by this equation, and we can use an SVD to find the optimal L using this equation. So solving L using depth D is very essential in our algorithm since it reduces a problem into a 1D line search. We only have to enumerate depth D, and given D, we solve for the optimal 3D line direction. We then project the 3D line segments back to each camera and compute the angle difference between the projected 3D line and the corresponding 2D line orientation. And the depth D that gives the minimum angle difference is the optimal value, which in turn gives us the optimal 3D line segments. So however, purely comparing the angle difference between the projected line and the 2D line is not accurate enough. So we propose a new feature for the correspondence, which we call light code. So for each camera, we use the visibility of the lights on each pixel as a feature. For example, in this image, each pixel encoded as a 36-bit string, where each bit represents whether it can be lit by that specific light. We can use the similarity of light code of 2 pixels to evaluate the level of correspondence between them. The underlying assumption of the light code is that whether a strand is bright or not is all the same across all cameras, although its intensity is view dependent. Now here is our full correlation function. We maximize both the light code correlation as well as the correlation between the 3D line direction and the projected 2D line. So here is how we compute the correlation of light code and angle difference. We run the algorithm on each pixel of each camera and produces millions of small line segments in 3D space. And after we got millions of small line segments, we follow the previous work to connect them into 3D hair strands. Sorry, I'm running a little bit over time. I'll try to be fast. So after that, we will reconstruct the hair reflectance. We divide it into two parts, the roughness estimation and the color estimation. So estimating the hair reflectance from purely images is a very ill-posed problem. So to keep problem trackable, we assume all hair strands have the same reflectance property and use an analytical and BRDF to model the reflectance. And the BRDF of hair strand consists of two parts, the longitudinal and the azimuthal components. And we only, so to make problems easier, we only estimate the longitudinal roughness. And even though it's still, these complications does not enable us to solve the problem. So in order to keep the problem solvable, we only use the pixel values of the line segments that are near the mirroring direction to fit the analytical BRDF. And here is a plot of measured BRDF and analytical BRDF. And as you can see, as the angle difference becomes larger, the measured BRDF becomes constant, which is caused by the interreflection between the hair strands. And that's why we only use a very limited region to fit the BRDF. And we estimate the color of hair strands using iterative procedure. So we render the hair in low resolution and compare the hair color with the ground truth capture image. And we then update the hair color parameter accordingly and re-render the hair. We iterate this process until the overall hair color matches the capture image. And usually it takes only 2 to 3 iterations. And here are some results. So here is the geometry reconstruction results. And here is our full rendering results where we reconstruct the geometry and the reflectance and then reword it into the images. And we are also capable of rendering hair with different colors. And so in conclusion, we have proposed a full pipeline for the hair inverse rendering given a set of photometric images captured on multiple cameras. And our limitation is that we cannot handle long or curly hair very well, and we can only reconstruct the visible hair strands, and we assume that the azimuthal roughness is a constant. And finally, I'd like to thank all groups and people who have helped the projects, and thank you everyone for their attention. Sorry, I'm a little bit running out of time.
All right, very nice work. Due to time minutes, does the audience have any questions? If there's no question, maybe we need to warm up for the next paper. All right, I think that's all. Let us thank the speaker again. Thank you.
Thank you.
So the last paper is called Single Image Full Body Human Relighting. The authors are Manuel Lagunas, Sun Xin, Yang Jimei, Rubin Villegas, Zhang Jianming, Shu Zhixin, Belen Mesa, and Diego Gonzalez. The Manuel will present his paper.
Can you hear me? Oh, okay, sorry. Yeah, so thanks for the introduction. My name is Manuel Lagunas. I'm a PhD student at Universidad Zaragoza inside the Graphics and Imaging Lab. I'm going to talk about our project called Single Image Full Body Human Relighting. This is a collaboration with Adobe Research. Okay, So let's imagine for a second that we are enjoying our holidays somewhere in Indonesia. We are at a beautiful beach and we want to take a photo of ourselves together with a beautiful landscape in a sunny day. Unfortunately, the sun is not in the best position and it casts some backlighting that does not allow us to take the best shot we could. It is our last day and we have to take that picture because our flight just departures in few hours. In this scenario, we could benefit from a post-processing tool that in an automatic or semi-automatic fashion would allow us to manipulate and control the lighting in the photograph to suit our needs. In this case, change the position of the sun in order to have a better illumination. If we look at these photographs, we see that illumination plays a central role in conveying the essence of the subject you need. Indeed, professional photographers will carefully control the lighting to manipulate the appearance of the subject in a photograph or just to give us different impressions. However, we are not always going to have a professional photographer with us, and in some scenarios, light conditions might not be ideal. Then we may end up just taking not the best shot. And those are the contexts where applying a post-processing step to modify the illumination in the photograph can enhance the way the light is interacting with the scene and provide a much better result. Such post-processing step is usually called relighting. Relighting aims at manipulating or changing the illumination in the scene to a different one while keeping other features of the subject, such as the geometry or the reflectance, the same. Therefore, our goal is going to be to create a framework capable of using an RGB image and some input illumination and to output a realistic relighting of the input image where the illumination has been modified and other features of the person are untouched. This is a challenging goal where we want to perform human relighting in the wild just from RGB image. And it's also a highly ill-posed problem where several factors such as geometry, illumination, or reflectance have to be disambiguated. The relighting problem is not new. Many people have proposed solutions to relight faces where the symmetric features and similar shape can be used for solving the problem. And also there has been different works, that aim to learn material, shape, and illumination in a scene, just from a set of sparse inputs. Or also, yes, they try to learn such decomposition for other domains that are different to humans. In our case, we aim to perform full-body human relighting from a single image, where we could have different poses or garments. Regarding human relighting, several solutions have been proposed. Many works use specialized complex hardware, consisting on a light stage where people is placed in the middle, and their appearances can be captured directly under different illuminations. However, this type of specialized hardware is expensive and not easily available. Closer to ours, the work of Kanamori and Endo proposes a relighting algorithm that directly uses RGB images. They assume materials to be Lambertian and leverage spherical harmonics lighting. In contrast, in our work, we model more complex reflectances and introduce a different image reconstruction formulation that in the end allows us for a more accurate relighting. Before we dive any deeper, let's introduce the background behind the relighting problem and how we model it. Interaction of light in a scene can be modeled through the rendering equation. Such equation tells us the amount of light or the amount of emitted radiance as an integral between the incoming light, the reflectance, the visibility, and the cosine term. In the case of human relighting, we want to separate the incoming light from all the other factors. Therefore, we can create a transport term, and the rendering equation has now the following form. Here, the term L has not changed, and now T represents the transport. We can leverage spherical harmonics lighting and precomputed radiant transfer to encode both the light and the transport as coefficients. Here, the letter Y represents the spherical harmonics basis, and the value L is their degree, while M is their order. This way, assuming the order L is infinite, we can reconstruct the original transport by having a weighted sum between the coefficients of the transport itself and the spherical harmonics. In addition, encoding the incoming light and the transport using the computed radiant transfer allows us to modify the rendering equation, where instead of solving a complex integral, now we have to do a dot product between the coefficients of the incoming light and the transport. Okay, now that we have grasped the background, we will talk about, and we know how to approximate the rendering equation, we can move on to how we develop our framework to reconstruct and relight images. First, we will talk about the reflectance model that we have used. Then we will discuss an inherent problem of spherical harmonics. And last, we will put everything together into our problem formulation. Previous work models the transport coefficient assuming materials to be Lambertian. This way, the dot product we have seen between transport and light to approximate the rendering equation becomes this, which allows us to split between albedo and shading. However, the Lambertian reflectance model is still limited. Instead, we model our transport by using an ordinary model for the diffuse and a Cook-Torrance GGX, and a Cook-Torrance model with GGX microfacets with the specular, or the specular, sorry. This way, our transport better captures specular reflections and directionality, which is visible in the insets on the figure of the right. And also, while the combination of those reflectance models may not be physically accurate, it does allow for additional artistic freedom and is also capable of better fitting real-world materials than if we would just consider a Lambertian model. Okay, now that we know how our reflectance model looks like, we will talk about an inherent problem of spherical harmonics. We have mentioned this equation before. It is used to encode incoming light into its coefficients. We have said that with an infinite value of L, we could reconstruct the original input. But as we can observe, we need actually a very large order of L to be able to reconstruct high-frequency details. One could directly reconstruct the image by doing an element-wise product between albedo and shading, as we have seen. But in order to account for errors in spherical harmonic lighting, we additionally introduce a residual term that does not represent any physical quantity and is instead directly learned to solve the errors for spherical harmonics. Okay, last we will talk about our image formulation. Our goal is to relight an image. We can introduce the relighting function R that uses the input image C and the target illumination L to produce a final relighted image. We have seen that for synthetic data, we could directly estimate such relighting function by solving this equation. However, for real photographs, the transport, illumination, or albedo are unknown. Therefore, we use a neural network that takes as an input the image and a set of parameters to estimate all those terms. In order to learn our neural network, the one that we just introduced, we could directly use late stage capture data. However, such hardware is not usually available. Instead, we rely on computer graphics and create a synthetic dataset of humans. Our dataset consists of 525 post-humans, where each model has a description of geometry and also includes materials in the forms of textures. We gathered 266 high dynamic range illuminations with a variety of indoor and outdoor scenarios, weather conditions, and so on. And we rely on path tracing and pre-computed radiant transfer to generate the final images. For each scene, we obtain its path trace image, the render image with pre-computed radiant transfer and spherical harmonics, alpha mask, shading, normal map, albedo, and a material properties image that encodes roughness, metallicity, and transparency. In the end, we generate all those maps for almost 100,000 scenes. Now that we know the background, the problem formulation, and the dataset, let's see how we learn our model. Let's recall the image formulation equation. Our goal is to generate from an input image all those intermediate terms that would then allow us to perform the relighting. We rely on a convolutional neural network in form of a unit with skip connections, where we have a short encoder and one decoder responsible for each of such intermediate terms. In the end, once we have all those terms predicted, we can directly approximate the relighting function and generate a new relighted image if a new illumination is given, or just reconstruct the input image with the estimated illumination. To train our model, we rely on the ground truth obtained data with the synthetic dataset. We use a combination of L1 and logarithmic losses that are directly applied to the predicted maps. And since using spherical harmonics and pre-computed radiant transfer is fully differentiable, we also propose a set of rendered losses for each of the reconstructed maps. Additional details can be found in the paper. Okay, now that we have our model trained, we can discuss the different results that we obtain. The following shows the ground truth image and the reconstruction obtained by our method. We can see how the per pixel L2 metric has actually low values. The shading obtained resembles its ground truth counterpart, and the albedo is also plausible, removing most information about geometry or illumination. Last, we have the residual term, which does not have a physical meaning, but seems to capture the directionality of the light in this case. Our model can also be used with real photographs. First, we compute and remove the mask from the input image. And then here we can observe the reconstruction that we obtained by our method. If we recall the image reconstruction equation, this would correspond to the R value using the light of the input image, directly estimated with our method. We can see that our model is capable of accurately reconstructing the input image with very low L2 per pixel error, and since we employ real photographs, no ground truth albedo or shading exists. This is another result that showcases another reconstruction with a pink coat. We can see again how our method achieves a faithful reconstruction of the input image with a low L2 per pixel error, and it's also capable of producing a plausible albedo, shading, and residual. Here we observe a comparison between our method and previous work. We see in each column the input image, the result, and those results from Kanamori and Endo. And we can see how we obtain superior performance and better approximate the input image. We are also capable of estimating a closer shading and albedo to the ground truth. On the right side, we can observe a comparison reconstructing the real photograph. We can see how we better capture the directionality of the light, and we also better estimate albedo. So far, we have seen results reconstructing the input image with the estimated light. In this video, we observe related results using new lights with input photographs. We can see how our method captures the geometry of the humans and also produces a realistic-looking relighting, according to the new illumination that is given. Additional video results are provided in the supplementary material, and please note that those are photographs and not synthetic inputs. However, our method is not free of limitation. We still suffer from the inherent problem of spherical harmonics lighting discussed before, and even though we try to avoid it with the residual term, it still poses a challenge. Also, more advanced reflectance models, such as, for instance, taking into account anisotropy in cloth or subsurface scattering for skin, could be taken into account. And last, some unsupervised learning techniques could be presented to avoid the need for large amounts of data. Last, we have presented a human relighting method that works in the wild just from RGB images. We aim to lift assumptions on Lambertian materials in the data that were present in previous work, and we finally introduce an additional residual term in our image formulation that allows us to better relight the input image. And that's all. I will now take questions. Thanks a lot.
All right. Thank you. Very good work.
Thank you.
And so let me ask the first question. So when I see you put even for the real images, you cut out the background region for the network.
Yeah.
So because actually the background image also you reveal some information about the light. Actually, it's a part of the lighting. So did you consider that because it's a neural network, they can try to infer something from the background? So did you try that using the background as part of input for your network?
It was definitely something we were considering on our discussions, because at the end, as you mentioned, the background adds some additional value, right? But we found out that when trying to fit the model, including the background was usually yielding worse performance than just making the model focus on the human itself. Probably a two-stage model where you could give the image with background just only to estimate the illumination, and the image without background to estimate all the other intermediate terms could have worked. That could be a potential line of to explore.
That makes a lot of sense. Yeah.
Thank you.
Well, so my second question is that it seems that you're using a rendering loss, right? So you use your decomposed maps and to render an image.
Yeah.
But actually the input is using the path tracing, while I believe the render will be different from that. So will that make a problem here?
So you mean the differences between the path trace result and the result, the path trace render and the render with the spherical harmonics and pre-computed radial transfer?
Yeah. There will be a residual, right?
Yeah, definitely. So there is a slight difference between the results using path tracing and spherical harmonics. It's true we render results with path tracing, but when we train our method, the images that we input are the ones that are rendered with spherical harmonics lighting and with pre-computed radial transfer. an extra step probably to the model as by means of future work could be to try to solve these inherent problems of spherical harmonics by adding an additional module that tries to bring the spherical harmonics rendering as the output of your model. It tries to approximate this to the path trace result, because at the end the path trace result is the one that it will be closer to real world, right? So what you could do is probably add some extra step, and probably an extra network that would take as an input your result with spherical harmonics rendering as we have presented, and then try to approximate the path trace result. That could be a potential line of future work. Yes, it would help you to avoid the problems with spherical harmonics lighting, and also try to fit to path tracing, to the path trace result.
Yeah, that makes a lot of sense to me.
Thank you.
Thank you for the presentation. I think that's all. So
thanks a lot.
That is another round of applause for all the speakers. Thank you for bringing us excellent work. So yeah, so for the audience, before you leave, and hope you enjoy a wonderful EGSR. This is the closing for the last session, but we still have the award ceremony and the closing section. And please check your email inbox, because there's a best presentation voting here. There's an instruction in the email, and you only have 20 minutes to vote. After 20 minutes, the closing session will announce the winner of the best presentation. And that's, I think, sum up for this session. And thank you for joining us.
Okay, it seems we're live now. Welcome to the closing and award session from my side. Again, Philipp Zalek here. Unfortunately, I actually have to apologize. Urgent things that happened this week, which made me have to travel actually today to a different place. So I couldn't actually attend that many sessions, but I did attend quite a few of them, and I heard lots and lots of good stuff. The sessions that I attended were amazing, and I heard very good feedback for this conference. So I think I can tell. So it's a great pleasure for me to thank everyone who was involved. Pascal and Goprit managed all of the OEA stuff, and with everyone else involved, together with Goprit, it's been working great. It's been in person, but I think we got as close to that as possible. Also, many thanks to everyone involved, and of course, the time to attend all of the talks and the great program that we put together for this year. So that's really all everyone involved, the paper chairs, the authors, of course, the organizers, everyone else that I probably forgot So yeah, thank you very much, and I think there's a few more interesting things, in particular the awards, so that will be interesting. Thanks from my side.
So I'd like to thank Philip and who just gave us they were wonderful hosts. They rolled with all of the challenges of having the virtual conference, and I'm very sorry that we couldn't be physically present in Saarland. Again, that was actually my first EGSR was in Saarland, so for me it would have been a wonderful homecoming. But I think we'll all be back there in 1 year, sooner or later, regardless. I also want to, again, as I said in the intro, thank Adrian. A majority of the wonderful things that happened with the papers program and the process are really due to him. He did more than his share of work this year, and it was wonderful to work with him. And I look forward to working with him again on something where maybe I can do him the favor that he did me this year. And I also am just so pleased with the OEA experience. This was I think largely due to what Pascal was doing behind the scenes and all his work on the website as well. This was the most smoothly run conference I've seen online, and that's entirely due to the organizers and Pascal and the OEA software really delivering. So a big round of applause to them. Thank you.
Thanks a lot. Thanks, Morgan, for your support. I also want to join you to thank the organizers. You all saw the very timely sessions, the way everybody could interact fluently. But what you didn't see is that in the backstage, Pascal and Gurpreet were always making all speakers and session chairs comfortable so that they could really focus on their talks, and I will not have to worry about any technical details. So there is a tradition at EGSR that when we have a physical conference, people will sign a little object so that the audience could give that to the organizers. We cannot do that physically, so we prepared a little virtual thank you card. So I'll post the link now to the chat. So Pascal, Gurpreet, you have and Philippe, of course, you'll have the time to look at what's been written. And for those who didn't have the time to add their own notes, I think the document is still open, so you can add your own post-its afterwards. So a big thank you again, because this was a very, very smooth conference, and it was very enjoyable.
Thanks. Also, a very big thank you from my side to you guys for always reacting quickly and smoothly to everything that needed to be organized. And of course, a big thank you to everybody who actually attended and actually used that system that we spent so much time trying to set up. And also a big thank you to the guys at OYE for actually replying to many of my questions, fixing quite a few bugs for me in very short time, and making sure that all of this actually runs smoothly and nicely. And with that, I think we can go forward with the awards, and I hand over to Elmer for that.
Takes a moment to share my screen here. 1 second. And I hope that it is now, oh, now it's up. Fantastic, thank you very much. So I have the great pleasure to welcome you to the awards sessions of this year's EGSR conference. And this award session is slightly special because we're going to have a couple of new awards this year that have not been given before. The goal behind this was to have more recognition for the work that is published at EGSR, because there's a lot of fantastic content that comes out of this conference, and also to highlight some of the exceptional contributions. Further, it hopefully increases the visibility of the conference in order to make sure that everybody sees what amazing work is done here. With this being said, also a big thank you to the organizers and the program chairs for making this fantastic conference possible. At this year's EGSR, we're going to hand out several awards as said. First of all, a Best Presentation Award that you have just voted on, and it's just fresh out of the press. Second of all, a Software and Dataset Award, and I'm going to say a few words about this a little bit later in this presentation. We have a Best Paper Award, and also this year an already established award which we decided that should be attributed more often, which is the Test of Time Award, to really give it to outstanding work that has been done at EGSR, and that has proven over a longer period of time. With this, let me jump in with the first award, the Best Presentation Award. This Best Presentation Award was decided by the audience, and you have done this in an anonymous vote, and the polls just closed, and in this very little short amount of time, people were very busy in the background in order to evaluate all these votes with scripts that were run, and then slides that were prepared at the very last moment and inserted into this presentation. I couldn't have done this with the help of the people that I mentioned here. Of course, Pascal has already received a lot of praise, but I think he didn't get enough yet, so I want to add to this as well. Without him sending out the right emails at the right moment in time, this wouldn't have been possible. And we have Matthijs Molenaar and Leonardo Scandolo, who worked hard on evaluating the votes at the final minute in order to present it. And of course, to you for voting. And so without any further ado, let me announce the winner of this year's presentation award. And it is Merlinimir David, Zhao Dong, Wenzel Jakob, and Anoka Planyan for their work on material and lighting reconstruction for complex indoor scenes with texture space differential rendering. I'm not sure if somebody of the authors is present in the audience, but congratulations on this award.
Thank you very much.
Yeah?
I am in the audience, yeah. Thank you so much.
Fantastic.
I wasn't expecting that.
Fantastic that you're here, because it was now a little bit on the spot and you were surprised, because this is really a result that we obtained 1 minute ago based on the online voting that we have put into place. Congratulations, and you will receive this award also in a metal plate that will be printed for you and sent to you after this conference.
That's super amazing. Thank you so much.
With this, thank you very much, and I move forward to the Software and Dataset Award. So this is a newly introduced award that was not handed out before. The idea is to recognize the effort and the commitment and also the strong contributions in the field, and also the need, and that is enabled by offering open source and publicly available data. The submissions could be made for about 2 months via a web page. It was announced on the mailing list of Eurographics, so if you're a member, that's the opportunity to get informed, and also on the webpage of EGSR. We had really a lot of high-quality suggestions, and it was very tough to choose the one candidate or the 2 candidates that would win this award. And therefore, I'm very happy that we had a very good committee of people that were put together in order to help with this decision. Markus Billeter from the University of Leeds, Abiyat Ghosh from Imperial College London, Vlastimil Hafran from CTU Prague, and Cem Yüksel from University of Utah. Let me start with the Software Award. This year's Software Award goes to a work that has been used throughout the graphics industry. It couples high-performance computing to an excellent API. And now you might probably guess it, it received an Academy Award for technical achievement, but is still freely available under Apache 2.0 license. I'm talking, of course, about Intel Embry. And with this, congratulations to the winners. And I believe that Philip Suzelek is present to receive the award on behalf of all the people involved in Embry. And of course, this is not just one person. This is a really gigantic group effort. With this, Philip.
Hello. Well, thank you very much. I hope you can actually hear me. I seem to have some Wi-Fi problems here. So
I believe you might be muted again, if I'm not mistaken, because of the... Yeah, now it's better.
Yeah, of course, they are the main people behind that, but that, of course, it goes back to some of the research that we did 20 years.
The connection dropped out, unfortunately, several times, and every time you come back, you were muted. But I believe that there are a lot of people to thank for this award that were involved in the development. Think of Ingo Wald, Carsten Valentin, Sven Woop, of course, a lot of people also in Saarbrücken. It's quite a coincidence that this award fell at the moment that it was organized in Saarbrücken. With this, congratulations again to everyone that is involved, and of course, many more names that I couldn't mention now. And then I would say we move forward to the next award. This is a Dataset Award. The Dataset Award that is given out this year is given to an enormous contribution in terms of reproducibility. It's not about big data, but about valuable and utilizable data. In particular, how many of you ever heard a reviewer tell you, try the dragon, use the bunny, or show the armadillo? Yeah, saying this out loud sounds a little bit strange, I admit, but yet we all know what it means because we come from the same community. And if a reviewer tells you this, you go to the one-stop shop to get your model in CG that is needed to convince everybody. And interestingly, this was not known to the committee, but when we collected all the votes, this is one of the entries that received a lot of remarks from people that wanted to see this work win the award. And so without any further ado, this year's Dataset Award goes to Special Effects for Computer Graphics Archive by Morgan McGuire. Congratulations. And I believe Morgan is here to say a few words.
Hi, thank you very much, Omar. Thank you to the community and to the committee for this award. I was certainly not expecting that. Creating open source and data for computer graphics is a labor of love for me, as many of you know. And this is really validated when I see them used in the impressive work that all of you have created. And so it's you know, it is meaningless to produce the data unless someone goes and writes a research paper using it. And so vicariously, I appreciate you letting me be a collaborator of yours. And I also want to acknowledge I'm joined in my goal of creating and sharing the further science by others from whose work I have personally benefited over many, many years. That goes back to Ingo Wald's data repository that at the beginning of my career I used heavily. Benedict Bitterly has a wonderful one now. And of course, code from MatMorpher and Wenzel Jakob, who essentially taught me how to program computer graphics through their open source. And finally, I'm pleased to say that to that very data repository, I have some new meshes coming for you just this month that have been about a year in production. And very excitingly, given the interest in neural geometry research at this conference, Tawaki Takakawa and Andrew Glassner and I collaborated, and we're about to release a new open source sign distance function dataset to the community in JCGT. So thank you very much.
Yeah, congratulations, Morgan, and really amazing work. We are all very impressed and happy that these kind of repositories exist, because we all make very, very much use of it. And it's also great that you mentioned all the other could have won this award, because it is indeed very, very difficult to choose the winners, because when we went over all the candidates, there's so much that could still be warranted this type of award in the future, that we are very happy that we now have this opportunity to do so. And we're happy to start with somebody who's so involved in the community and gave so much over all these years. Thank you very much. With this, let me move over to the Best Paper Award. As you know, here it's a little bit the same. There are so many very good papers, and I have to say this year I was particularly impressed. It's very difficult to make a suggestion. Should we pick it out of this session or that session? Basically, there was high quality work everywhere. In order to make this work a little bit feasible, we looked at the top evaluations by the reviewers, because there is a thorough review process with EGSR, and then also took the best paper suggestions by the reviewers into account. This was new this year, that reviewers could indicate which papers potentially could win such an award. We also looked for creative and novel ideas and potentially high impact. In order to make this decision, I'm happy I didn't have to be the one that has to decide everything here. We have a strong committee behind that helped in the selection of this year's winner. Tammy Bubecker from Adobe, Michael Wimmer from the TU Wien, and Johannes Schudaiske from Karlsruhe Institute of Technology. With this, let me move forward to the Best Paper Award of EGSR 2021. The Best Paper Award goes to, before that, one word of our sponsor. Yeah, I know it sounds a little bit like advertisement, but I think it's very important to underline when companies really make the effort to support our community. And in this case, I want to mention that NVIDIA supported us by offering a graphics card to the winner of this year's Best Paper. And now comes the important message here. It's not going to be one graphics card. In fact, the committee had such a hard time with all these high quality submissions that we decided to hand out 2 Best Paper Awards this year at this conference. With this being said, let us have a look at who won. The work that I'm going to talk about addresses porous materials in a sound and convincing mathematical way. The paper provides a practical real-time approximation that will surely find widespread use. Spherical Lambertian representations extend the space of analytical material models, and the committee is convinced that it will pave the way to much future work. With this, congratulations. Oh, I see that I made a mistake and I already gave away the next winner. Congratulations to Eugene Dion for winning this year's Best Paper Award. Unfortunately, Eugene cannot be here. You saw probably his message on the chat. He's currently in New Zealand, and there it's very, very deep in the night. But we will surely make sure that he will get his Best Paper Award sent to him by mail. The second winner this year is a paper that is presenting a new mathematical tool. It's about building really nice landscapes with perfect lighting included. And it uses moving basis decomposition that generalizes many existing linear basis decomposition methods. It is highly scalable and has many potential applications, most impressively demonstrated with pre-computed light transport. The paper presents the theory and solver to obtain suitable moving basis decomposition and opens up many exciting possibilities in the future. Thank you very much. Congratulations for this award. And I believe Ari is in the audience and wants to say a few words.
Hi, thank you. I think there were a number of really good papers this year, and I think EGSR was the first conference I ever attended. So in that way, this is very special to me. And I think the organizers, reviewers, paper authors, and all the attendees made for a great conference this year. So thank you very much.
Thank you. Congratulations. And let us move on to the last award of the day. And that is, on the other hand, a very important award, the Test of Time Award. Test of Time Award has the goal to recognize outstanding scientific achievements. It should have exceptionally high impact in industry and/or academia, and the work has to be proven its quality over a longer period of time, at least 10 years after its publication. The ideas should be substantially transforming the community, and in this case, the EGSR steering committee voted a list of candidates to select this year's winner. The Test of Time Award goes to a technique or a method, a paper, that explains how to generalize standard reflection microfacet theory to refraction. This was the main question of the paper that received this year's Time Award, but as you can see, the results were really, really stunning already for a paper out of 2007. Yet, its very high citation count is not only based on the answer to this question of how to generalize standard reflection microfacet theory to refraction, but there was another element in this paper that truly revolutionized graphics around the world. It is now used in almost all major graphics applications and engines. The GGX microfacet distribution with its long tail that allowed for more realistic reflections. They derived all the necessary details for its implementation and presented steps in a nice and intuitive geometric interpretation. Even an explicit equation, equation 14 from the paper, has been cited multiple times in the follow-up literature when referring to the derivation of the specular microfacets. Finally, the work is even rounded up with comparisons against real material acquisition to show the full potential of this work. And here you can see many different models compared to each other, and you see the breadth of results that you can obtain with this type of technique. The Eurographics Symposium on Rendering proudly presents this year's Test of Time Award, which is attributed to Bruce Walter, Steve Marshner, Hong-Sung Lee, and Ken Torrance for the work Microfacet Models for Refraction Through Rough Surfaces. Congratulations. And I believe Steve Marshner is here to say a few words.
Thank you. We're really surprised and pleased to learn about this award. Bruce is on vacation and we haven't been able to reach him, so I'm here by myself. But thank you so much. I want to say that this is one of the papers that is in my list of publications that I personally have gone back to look at more times than many, and it's really because of Bruce's beautiful presentation of the model that brings me back to this. And I think it's very true that the quality of the presentation as well as the introduction of this GGX or Trowbridge-Wright's distribution is something that Bruce is really the prime. He was the prime mover on that part of the paper, so I really want to give him the spotlight here, even though he's not here. And it was a wonderful opportunity to be guided by Ken Torrance one of the last times, by his wisdom both on the measurement side and on the modeling side. And I have to say that I presented this at EGSR that year, and I just really feel like EGSR is absolutely the perfect place for that paper to be presented. It's the audience that really cares about it, that wants to hear about the details of reflection models, and so I think I really want to thank, I guess, everyone who's made EGSR what it is over the years to provide that perfect place for the paper to be. So, thanks very much again.
Absolutely, congratulations. And with this, that closes our awards ceremony for this year. I hope that you enjoyed it. Thank you very much again for your attention, and also congratulations again to all the winners of this year, and also the people that couldn't win but still provided this amazing work that has made up this fantastic conference. With this, I would give back to the organizers, and thank you very much.
Yes, and that's pretty much all that we have in store for you. Do feel free to keep using OEA to mingle and socialize, and I'm looking very much forward to meeting all of you guys in person again next year.
In Prague.
In Prague.
Yeah, thanks a lot, guys. Have a nice one. Yeah.